Hello there and welcome to Science for Sleep, where curiosity gets cozy, the lights of the universe are turned down a little, and science is allowed to take the long, quiet route toward rest. Tonight, we're going to visit something so small and so faint that calling it a galaxy almost feels like calling a single candle a city. Its name is Ursa Major 3/UNIONS 1, often shortened to UMA 3/U1, and it may represent the smallest and least luminous galaxy humanity has ever found. Or it may be an unusually fragile star cluster that happens to sit exactly on the border between two kinds of object. Astronomers are still working that out, which makes this tiny gathering of ancient stars even more interesting. It is not simply a record holder waiting to be measured and placed neatly in a catalogue. It is a question hanging in the outskirts of the Milky Way, asking how little a galaxy can contain before it stops being a galaxy at all. Before we move closer, where are you listening from tonight? Perhaps it is already dark outside your window, and the familiar stars are beginning to appear. Maybe you are hearing this during a quiet afternoon, or while rain taps against the glass, or while the rest of the house has finally settled down. And what time is it where you are? Somewhere above the northern sky, in the direction of the Great Bear, there is a collection of stars so faint that no unaided human eye could ever recognize it as a separate system. Yet those stars have been moving together for billions of years, carrying a history that began long before the sun existed. If you find these slow journeys through astronomy soothing, or if you simply enjoy ending the day with a mystery that is much larger than tomorrow's to-do list, you can gently tap the like button and subscribe. It helps this quiet corner of science reach other listeners who may also enjoy falling asleep while wondering about dark matter, ancient stars, and why astronomers insist on giving one object two names. There is a sensible reason for that last one, although astronomy does occasionally resemble a household in which everyone has labelled the same storage box differently. Now settle in and let the scale of the Milky Way become familiar for a moment. Our galaxy contains hundreds of billions of stars spread across a broad disk, roughly 100,000 light-years wide. It has spiral arms, giant clouds of gas, clusters containing hundreds of thousands of stars, and a central black hole with a mass millions of times greater than the Sun. The Milky Way is not merely a collection of lights. It is an enormous gravitational system with a long history of collisions, mergers, births, deaths, and slow rearrangements. The Sun travels through this system with planets, moons, asteroids, and one species that spends a surprising amount of time checking whether it has received any new messages. Against that scale, UNIONS 1 seems almost unreasonable. The original Discovery study estimated its total visible light at only about 11 times the luminosity of the Sun, with an absolute visual magnitude of approximately plus 2.2. Its half-light radius is roughly 3 parsecs, or around 10 light-years, meaning that half of its light comes from within a region smaller than many ordinary stellar neighbourhoods. The system lies about 10 kiloparsecs from the Sun, approximately 33,000 light-years away, and its known population is ancient and extremely poor in heavy elements. Early observation suggested an age greater than 11 billion years. It was uncovered in data from the Ultraviolet Near-Infrared Optical Northern Survey, known as UNIONS, and then examined spectroscopically with instruments at the Keck Observatory. A galaxy with only a handful of visible members sounds like a contradiction. We are accustomed to galaxies arriving in grand sizes. Even dwarf galaxies can contain thousands, millions, or billions of stars. The word galaxy encourages the mind to picture a glowing spiral, a bright elliptical cloud, or at least a hazy patch with enough stars to look crowded. UNIONS. One does none of that. In ordinary images, it does not announce itself with a visible shape. It does not resemble a miniature Milky Way. It appears as a sparse sprinkling of points that could easily be mistaken for unrelated stars in the foreground and background. That is part of what makes the discovery so impressive. Finding a bright galaxy is sometimes like noticing a lighthouse. Finding UNIONS 1 is more like identifying a few grains of pale sand on a beach, and realizing that they have been traveling together for most of cosmic history. Astronomers did not simply look through a telescope and see a tiny glowing island. They searched enormous sets of survey data for a slight excess of stars with compatible colours, brightnesses, distances, and motions. The signal was not a bold object standing apart from the sky. It was a statistical whisper. The name itself tells us something about the uncertainty. Ursa Major places the object among satellite systems associated with the constellation Ursa Major, while UNIONS 1 connects it to the survey in which it was identified. The double name is useful because astronomers have not yet reached complete agreement about what the system is. If it is a dwarf galaxy, Ursa Major 3 is an appropriate galactic designation. If it is a star cluster, UNIONS 1 may be the more suitable label. So the object carries both names while the evidence is weighed, rather like someone arriving at a formal event wearing two name badges, because no one has decided which department they belong to. At first, the case for calling it a galaxy looked especially intriguing. The Discovery team measured the motions of a small number of probable member stars. Those stars appeared to have a larger spread in velocity than such a tiny visible system should produce through the gravity of its stars alone. If that measurement represented the true internal motion of the system, something unseen would have been supplying most of the gravitational mass. The natural candidate was dark matter. That would make UNIONS 1 an extreme dwarf galaxy. Very little starlight embedded in a much more massive invisible halo. This distinction matters because a galaxy is not defined only by having many stars. Some of the smallest known galaxies contain fewer stars than a large star cluster. The most useful dividing clues often involve dark matter and chemical history. A dwarf galaxy generally forms inside a dark matter halo and may preserve evidence that its stars were born over more than one episode. A star cluster is usually dominated by ordinary matter and often contains stars formed from the same original cloud at roughly the same time. The boundary becomes difficult when an object is faint, compact, ancient, and represented by only a small sample of measurable stars. At that point, nature has not necessarily provided the labels that human catalogues would prefer. For a while, UNIONS 1 seemed capable of becoming the most dark matter-dominated galaxy ever recognized. Simulations published after its discovery argued that a system with so little ordinary stellar mass might struggle to survive repeated passages through the Milky Way's gravitational field unless it were protected by a dense dark matter halo. The Milky Way does not need to collide directly with a satellite to damage it. Its gravity can pull more strongly on the near side than the far side, creating tidal forces that stretch and strip a small object. A fragile group of stars orbiting our galaxy can gradually lose members until it becomes a stream, a faint trail, or nothing that can still be identified as a single system. Early modelling suggested that a purely stellar version of UMA 3/U1 might survive only around one orbit, roughly 400 million years, making its present existence seem surprisingly fortunate. Dark matter offered a tidy explanation. Place the visible stars inside a larger invisible structure, and the object could remain bound despite the Milky Way's pull. It would be a galaxy reduced almost to its minimum visible form, not a grand city of suns, but a tiny occupied room inside a much larger dark building. The stars would be the only lamp switched on. Everything else would reveal itself through gravity. That possibility carried consequences beyond the object itself. Modern cosmology predicts that galaxies form inside halos of dark matter. Large halos gather gas efficiently and build large galaxies. Smaller halos may form dwarf galaxies. Still smaller ones may fail to make many stars, especially after the early universe was filled with radiation that heated gas and made it harder for tiny halos to hold onto the material needed for star formation. Astronomers therefore expect the Milky Way to be surrounded by many low-mass dark matter structures, some bright enough to host visible satellites, and many possibly almost dark. If UNIONS 1 were confirmed as a true galaxy, it could help locate the lower limit of that process. How small can a dark matter halo be and still produce stars? How few stars can remain while the system continues to count as a galaxy? Could many similar objects be orbiting nearby, hidden not because they are far away, but because they are barely luminous? A system containing only dozens of detectable stars could be the visible edge of an enormous unseen population. Then the story changed, as good scientific stories often do. New observations examined more member stars, repeated velocity measurements, and looked for signs of chemical variation. A later analysis covering 16 probable members found that the original evidence for a large internal velocity spread had weakened. One star turned out to be a binary, meaning its measured speed could be altered by motion around a companion rather than motion through a massive dark halo. Higher precision data also shifted some of the velocities close together. The newer study reported no positive observational evidence for dark matter and found no large metallicity spread among the measured stars. Those results lean more naturally toward a star cluster interpretation, although they do not completely rule out a dwarf galaxy. This is an important point to keep beside us throughout the journey. The title, The Smallest Galaxy in the Universe, describes the extraordinary possibility that made UNIONS one famous, but its identity remains unsettled. As of the latest published work, many researchers consider a star cluster more likely. That does not make the object less valuable. In some ways, it makes it more useful because it forces astronomers to examine what they mean when they use the word galaxy. It also shows how science behaves when new evidence arrives. The earlier measurements were not foolish, and the later measurements do not make the discovery uninteresting. A small sample can produce a tentative picture. A larger and more precise sample can change it. That is not science failing to make up its mind. It is science refusing to pretend that uncertainty has disappeared. There is something reassuring about that, especially at the end of a long day. We often imagine scientific knowledge as a warehouse filled with facts, each one packed in a labelled box and placed on the correct shelf. In reality, the edges of knowledge look more like a work table. Measurements are checked, labels are crossed out and rewritten. One model explains a result, another model reproduces it differently, and everyone keeps looking for the observation that will separate the two. Occasionally, someone discovers that a particularly important star has a companion and has been tugged back and forth during the entire discussion. The star cluster possibility has gained support from computer simulations as well. Newer models that include stellar evolution, binary stars and compact remnants suggest that a dark matter-free cluster resembling UNIONS one may survive for much longer than the earliest estimates indicated. White dwarfs, neutron stars, and perhaps stellar mass black holes can add mass without adding much visible light. Over time, a cluster can preferentially lose low-mass stars while retaining some heavier remnants near its centre. The object would then appear unusually faint for the amount of gravitating material it contains, even without a dark matter halo. One modelling study estimated a remaining lifetime of roughly 2.7 billion years for such a cluster, making its survival less improbable than originally thought. Notice how delicately the argument turns. Invisible mass does not automatically mean dark matter. Ordinary stars can become faint remnants. Binary motion can imitate a velocity spread. Tidal disruption can disturb a system that is not in equilibrium. With only a small number of observable members, each star matters enormously. In the Milky Way, removing one star from a calculation would be like removing a single grain of flour from a bakery. In UNIONS 1, it can change the inferred nature of the entire object. Even its brightness invites unusual comparisons. The combined visible light of this satellite is comparable to only a small group of sun-like stars. If all of its light could somehow be gathered and viewed from the standard distance astronomers use to define absolute magnitude, it would not look like a majestic galaxy. It would resemble a moderately bright star. Of course, the light is not coming from one object. It is divided among an old sparse population spread across several light years. Seen from Earth, those members are mixed with other stars along the same line of sight, which is why the system remained hidden until deep surveys and careful statistical searches brought it into view. The phrase smallest galaxy can also be misleading because there are several ways to be small. A galaxy can have a small physical radius, a low stellar mass, a low total luminosity, or a small number of known stars. UNIONS 1 is extreme in several of these categories, but astronomy rarely offers a single clean ruler. Some compact galaxies are physically small but contain many stars. Some diffuse galaxies stretch over large areas while producing very little light. Some satellite systems are so faint that their total properties must be inferred from a handful of members. Comparing them is not like lining up 10 pebbles and choosing the shortest. It is more like comparing a snowflake, a soap bubble, and a very small sandwich, then being asked which one is the least substantial. Still, there is no need to hurry past the wonder of it. Whether UNIONS 1 is a galaxy or a cluster, these stars appear to be survivors from the early history of the universe. Their low abundance of elements heavier than hydrogen and helium tells us that they formed before many generations of stars had enriched space with carbon, oxygen, iron, and the other materials that later became planets and people. They belong to an older chemical era. The atoms inside them have spent more than 10 billion years taking part in a quiet gravitational arrangement, while the Milky Way grew, merged with smaller systems, formed its disk, produced the sun, and eventually developed astronomers who would notice them. Imagine the history those stars have passed through without needing to imagine that they were conscious of any of it. They formed when the universe was much younger. The Milky Way was still assembling. Massive stars elsewhere lived quickly and exploded. Galaxies collided, new elements accumulated. The Sun appeared only about 4.6 billion years ago, meaning the stars of UNIONS 1 were already ancient when our solar system began. Earth formed, cooled, produced oceans, life, forests, dinosaurs, mammals, radio telescopes, and fitted sheets that never fold as neatly as expected. Through all of that, the small system continued along its orbit. Its position also reminds us that the Milky Way does not end at the bright disk visible in photographs. The galaxy is surrounded by a large halo containing old stars, globular clusters, streams left by disrupted satellites, dwarf galaxies, gas, and dark matter. The outskirts are not empty, they are simply sparse. Small companions travel there on long orbits, some intact, some being pulled apart, and some so faint that we have only recently developed the surveys needed to detect them. UNIONS was designed to examine the northern sky deeply and across a wide area by combining observations from major facilities, including the Canada-France-Hawaii telescope and Pan-STARRS. Surveys like this do not always know in advance what they will find. They build careful maps with enough depth and consistency that unusual patterns can emerge later. The discovery of UMA3/U1 came from recognizing one of those patterns, then checking it with spectroscopy to see whether the stars were genuinely moving together. A possible galaxy entered human knowledge not as a dramatic flash or a new point suddenly appearing, but as a subtle arrangement that had been present in the data, waiting for someone to ask the right question. That method may lead to more discoveries. If one object this faint exists close to the Milky Way, others may exist as well. Some may be genuine galaxies wrapped in dark matter. Others may be nearly dissolved star clusters. There may be a whole population occupying the uncomfortable middle ground, where the familiar categories break down. Future surveys capable of repeatedly imaging large portions of the sky with great sensitivity should improve the search. Better spectroscopy will also matter, because measuring the motions and chemistry of such faint stars is difficult. The problem is not merely finding more points of light, it is learning which points belong together and what their shared history has been. For tonight, we can allow UNIONS 1 to keep both of its identities. We can treat it as a candidate for the smallest galaxy known, and also as a possible star cluster unlike any other. There is no need to force the answer before the observations are ready. The uncertainty is part of the subject. It gives us a way to explore dark matter, stellar evolution, the tidal pull of the Milky Way, ancient chemical composition, and the human habit of drawing borders around things that nature may have placed on a continuous spectrum. A galaxy does not need spiral arms. It does not need glowing clouds or a central black hole that appears in dramatic illustrations. At the faintest end, it may need only a dark matter halo, a shared gravitational history, and enough stars to reveal that something is there. A cluster, meanwhile, can become so old, stripped, and dominated by faint remnants that it begins to imitate some of those same signals. UNIONS one stands between the definitions, barely visible and scientifically inconvenient, which is often where the most useful objects are found. So, as you settle more deeply into the quiet, picture the northern sky not as a flat arrangement of familiar constellations, but as a view through the broad outskirts of our galaxy. In the direction of Ursa Major, beyond the nearby stars that draw the Great Bear, a tiny ancient system follows its path around the Milky Way. It does not glow like the galaxies shown on posters. It would not catch your eye through a garden telescope. Even professional instruments needed survey depth, careful filtering, and follow-up measurements to separate it from the crowded sky. Although UNIONS one is often introduced as the smallest possible galaxy, its most remarkable quality may be how easily it could have remained unknown. It is close enough to belong to the Milky Way's immediate neighbourhood, at least by galactic standards, yet it does not look like a galaxy in the familiar sense. There is no bright central glow, no spiral pattern, no broad oval of unresolved starlight, and no obvious boundary separating it from the rest of the sky. A photograph of the region does not present a tiny island of stars waiting to be circled with a pen. It presents a normal-looking field filled with points of light, most of which have nothing to do with one another. That creates a problem which sounds simple until you try to solve it. How do you discover an object when its individual stars are visible, but the object made from those stars is almost invisible? Imagine looking across a crowded railway station and being asked to identify a family whose members are standing far apart, wearing ordinary clothes and giving no obvious sign that they arrived together. You might notice each person, but recognizing the group would require more information. You would need to know that they came from the same direction, were moving toward the same platform, and perhaps shared a few subtle features. Astronomers face a similar task when searching for the faintest satellites of the Milky Way. A large galaxy can be detected through the combined light of enormous numbers of stars. Even when its individual stars cannot be separated, their blended glow creates a visible shape. UNIONS one sits at the opposite extreme. Its total luminosity was estimated to be equivalent to only a few tens of suns, and its original inferred stellar mass was roughly 16 times the mass of the Sun. The system's absolute visual magnitude was measured at about plus 2.2, making it less luminous than many single stars visible in the night sky if all objects were placed at the same standard distance. It is compact as a system, with a half-light radius of about 3 parsecs, but compactness does not help very much when there is hardly any light to compact. To understand how extreme that is, think about what happens when you look at the Milky Way from a dark location. The pale band across the sky is produced by the combined light of countless distant stars. You cannot distinguish most of them individually, yet together they create enough brightness for your eyes to notice the galaxy as a continuous feature. UNIONS one does not have enough luminous material to make that kind of impression. Its stars remain separate points, scattered across a small patch of sky and mixed with foreground stars belonging to the Milky Way's disk and halo. The system is not hidden behind a curtain. It is hidden by resemblance. Its members look too much like ordinary stars that happen to be in the same direction. This is one reason the faintest galaxies were not found in the same way as bright galaxies. Early galaxy catalogues were built largely from objects that appeared extended, fuzzy, or visibly distinct on photographic plates. a spiral galaxy could reveal itself as a smudge. An elliptical galaxy could appear as a smooth patch. Even many dwarf galaxies produced enough unresolved light to be recognized as low surface brightness objects. But as searches moved towards smaller and fainter satellites, astronomers increasingly had to stop looking for glowing shapes and start looking for patterns among individual stars. The crucial phrase here is surface brightness. Total brightness tells you how much light an object produces altogether. Surface brightness tells you how thinly that light is spread across the sky. Two objects can emit the same total amount of light while looking very different. Put the light into a compact point and it may stand out clearly. Spread it across a wide area and it can fade below the brightness of the background. A handful of glow-in-the-dark stickers placed on top of one another would be noticeable. The same stickers distributed across an entire garden might disappear unless you knew exactly where to search. UNIONS 1 is physically small, yet its total light is so low that there is no dependable diffuse glow to announce it. Astronomers instead search for an overdensity, meaning a region containing slightly more stars of a particular kind than chance would normally provide. The word overdensity may sound dramatic, as though the sky has developed a traffic jam. In practice, the excess can be slight. A search algorithm may examine millions or billions of stellar detections and notice that one tiny area contains a few more stars consistent with an old, metal-poor population at the same distance. Those qualifications are essential. Simply finding several stars near one another is not enough. Stars overlap in our line of sight all the time. A nearby red dwarf, a distant giant, and a much farther halo star can appear almost side by side even though they are separated by thousands of light years. The sky is a two-dimensional view of a three-dimensional galaxy, so unrelated objects are constantly projected onto the same patches. A convincing candidate emerges only when the stars fit a common pattern. One of the most useful patterns comes from a color magnitude diagram. Astronomers measure how bright each star appears through different filters, then compare brightness with color. Color carries information about temperature, while brightness, once distance and stellar evolution are considered, helps indicate a star's stage of life. Stars born at roughly the same time and with similar chemical composition arrange themselves along recognizable sequences. A sparse ancient system may reveal a few stars lying along the expected main sequence, turn-off, or giant branch of an old population. Individually, those stars seem ordinary. Together they begin to resemble a shared history. This is rather like finding a few loose pieces from the same jigsaw puzzle. One blue piece means very little. Several pieces with the same shade, texture, and edge pattern suggest that they belong to one picture. Astronomers use theoretical stellar populations, often called isochrones, as guides showing where stars of a certain age, chemical composition, and distance should appear on the diagram. They can then search wide survey catalogues for places where the sky contains more stars near that guide than expected from the surrounding field. The Discovery team identified UNIONS 1 in the deep, wide-field ultraviolet near-infrared optical northern survey. The data were sensitive enough to reveal faint stars across a large region of the northern sky, which is exactly what is needed for objects that are both inconspicuous and impossible to locate in advance. A narrow but very deep telescope image might miss the system simply because it looked in the wrong place. A very wide but shallow survey might cover the correct area, while failing to detect enough of its low luminosity members. Finding systems like this requires both reach and coverage, the ability to examine a great deal of sky while still recording faint points accurately. Even then, an overdensity is only the beginning. The sky is full of statistical accidents. Random stars can form temporary-looking clumps, particularly when a survey contains enormous numbers of sources. Dust can alter apparent colours and brightnesses. Small differences in image quality can affect how many faint stars are detected in one region compared with another. Distant galaxies may be mistaken for stars if they appear almost point-like. Electronic noise, diffraction patterns around bright stars, and imperfections in data processing can all create false signals. A computer can point to a suspicious patch, but suspicion is not the same as discovery. Astronomers therefore compare the candidate region with nearby control fields. If the surrounding sky contains a similar number of stars with similar properties, the supposed satellite may vanish under closer inspection. They also model the object's spatial distribution. A genuine stellar system should usually show some concentration toward a centre, even if the centre is weak and only statistically defined. Researchers estimate quantities such as angular size, ellipticity and half-light radius, while also accounting for contamination from unrelated stars. For UNIONS 1, this work was unusually delicate because the system contains so few observable members. In a rich cluster, changing the membership of one or two stars has almost no effect on the overall picture. In a system near the limit of detectability, one star can influence the measured size, luminosity, shape and velocity dispersion. A bright probable member may contribute a significant fraction of the total inferred light. An interloper mistakenly included in the sample can make the system seem more extended or dynamically hotter. Conversely, excluding a genuine member can make it seem even smaller. This means the object almost disappears in a mathematical sense as well as a visual one. Its estimated properties are not read directly from a crisp outline. They are reconstructed from probabilities. Each star may be assigned a likelihood of membership based on its position, colour, brightness, motion across the sky, radial velocity and chemical composition. Those probabilities are combined into a model of an object no one can simply point to and see as a complete shape. Gaia measurements add another piece of the puzzle. Gaia has mapped the positions, distances and motions of enormous numbers of stars, although the faintest stars remain difficult or impossible for it to measure precisely. Proper motion describes a star's slow movement across the sky. If several stars near one another share a similar proper motion, that supports the idea that they belong to one travelling system, rather than forming a chance alignment. In the original follow-up of UNIONS 1, 8 of the 11 stars identified through radial velocity also had full Gaia astrometric information and were consistent with moving together. That shared motion helped confirm that the overdensity represented a real Milky Way satellite, even while its classification remained uncertain. Radial velocity provides motion along our line of sight. Astronomers obtain it by spreading starlight into a spectrum and measuring small shifts in known absorption lines. When a star moves toward us, its spectral features shift slightly toward shorter wavelengths. When it moves away, they shift toward longer wavelengths. The changes are tiny, but precise instruments can turn them into velocities. If stars in the candidate region cluster around a common radial velocity, the case for a shared system becomes much stronger. The Keck 2 telescope and its Deimos spectrograph were used to examine stars associated with UNIONS 1. This was not a matter of taking one grand portrait. Spectroscopy gathered detailed light from selected targets, allowing the researchers to compare velocities and estimate chemical properties. 11 radial velocity members were identified in the discovery work. That number is enough to establish an intriguing system, but it is also small enough that every measurement must be treated carefully. Binary stars make the task harder. Two stars orbiting each other change their line of sight speeds as they move around their common centre of mass. If one member of a binary is observed only once, its measured velocity may not represent the motion of the binary system through the galaxy. It may include the star's temporary orbital motion. In an object with hundreds or thousands of measured stars, binary effect can often be modelled statistically. With a sample of roughly a dozen, one binary can inflate the apparent spread of velocities and create the impression of extra unseen mass. That issue later became important for UNIONS 1. Additional observations found that one relevant star showed velocity variability consistent with being in a binary system. More precise multi-epoch measurements also reduced the evidence for a large internal velocity dispersion. By 2025, a follow-up analysis reported no positive observational evidence requiring dark matter, and no large metallicity spread among the measured stars, making a star cluster interpretation more likely, though not absolutely proven. The object had not disappeared from astronomy, but one of its most dramatic possible identities had become less certain. There is a useful lesson in that change. Detection and interpretation are separate stages. Astronomers can be confident that a group of stars forms a genuine satellite, while still debating what kind of satellite it is. UNIONS 1 is real as a coherent stellar system. The unsettled part is whether its gravity is dominated by dark matter, faint stellar remnants, ordinary low-mass stars, or some combination that has been altered by the Milky Way's tidal field. The phrase, almost disappeared, also applies physically. A tiny satellite orbiting the Milky Way lives in a dangerous gravitational environment. Our galaxy pulls on every part of it, but not equally. The side closer to the Milky Way feels a slightly stronger attraction than the side farther away. Across a large, massive object, its own gravity can resist this difference. Across a small system with very little mass, the unequal pull can gradually remove stars. As stars escape, the remaining system becomes fainter. Its outer regions thin out first. Escaped members may form narrow tidal tails that stretch along the orbit. After enough time, the central concentration can weaken until the object is no longer recognizable as a bound cluster or galaxy. Its stars do not vanish. They join the Milky Way's halo, becoming isolated points mixed with countless others. The satellite disappears as an identifiable relationship. This is one way the Milky Way grows. It absorbs smaller companions, not always through a single violent collision, but through repeated gravitational stripping. Long streams of stars found throughout the halo are the remains of systems that have been pulled apart. Some streams come from dwarf galaxies, others from globular clusters. They preserve the path of a former object after the object itself has been largely erased. Early simulations of UNIONS once suggested that a system made only of its small, visible stellar mass would be unlikely to survive for long in its present orbit. A lifetime of roughly one orbit, around a few 100 million years, made the discovery seem suspiciously well-timed. Either it was protected by a dense dark matter halo, or humanity happened to notice it during the brief closing stage before complete disruption. That argument strengthened the original interest in the object as a possible ultra-faint galaxy. Later models showed that the cluster possibility may be less improbable than first thought. When simulations include stellar evolution, binary stars, mass segregation, and compact remnants such as white dwarfs, neutron stars, and black holes, the remaining system can contain more gravitating mass than its visible stars suggest. Low-mass luminous stars may be preferentially lost, while heavier dark remnants remain concentrated toward the centre. One 2025 study found models capable of resembling UNIONS, one without a dark matter halo, and estimated a remaining lifetime of about 2.7 billion years. Another study explored how a central subsystem of stellar mass black holes could help produce a high apparent mass-to-light ratio in an extremely faint cluster. So the object may have nearly disappeared in at least 3 different ways. It almost disappeared from our surveys because it did not produce a visible galactic glow. It may be in the process of physically losing stars to the Milky Way, and its proposed identity as the smallest dark matter-dominated galaxy nearly disappeared when better measurements weakened the original dynamical evidence. Yet the remaining system is still there, still scientifically valuable, and still forcing astronomers to examine the boundary between star clusters and galaxies. The difficulty of seeing it also tells us something uncomfortable about our galactic neighbourhood. Discovery does not depend only on what exists. It depends on what our instruments and search methods are prepared to recognise. Bright satellites were found first because they were obvious. Diffuse satellites required better imaging. Ultra-faint systems required large digital surveys, colour-based filtering, statistical searches, precise astrometry, and spectroscopy. Objects even fainter than UNIONS may remain undetected because they contain too few stars above present survey limits, lie in crowded regions near the Milky Way's disk, or sit behind areas of heavy dust. The northern and southern skies have also been surveyed with different instruments, depths and histories. A system's chance of discovery can depend on where it happens to appear from Earth. Near the galactic plane, dense foreground populations make it harder to identify weak overdensities. Dust dims and reddens background stars. Farther into the halo, the field may be cleaner, but the satellite stars become fainter with distance. There is no perfectly easy place to hide, but there are many places where hiding is easier. Selection effects then shape the catalogue we use to understand galaxy formation. If astronomers detect only satellites above a certain brightness or size, the observed population may look different from the real one. The faintest known object is not necessarily the faintest object that exists. It is the faintest one that happened to be detectable with available data, algorithms, and follow-up resources. UNIONS, one may therefore mark an observational frontier rather than a physical limit. That distinction matters for dark matter theories. Cosmological models predict large numbers of low-mass dark matter halos around galaxies like the Milky Way. Not all of those halos are expected to form visible stars, and those that do may be extremely faint. Counting satellites helps test how small-scale structure developed, but the count is useful only if astronomers understand how many systems have been missed. Every discovery near the survey threshold helps improve estimates of completeness. It tells researchers what sorts of objects can be found, and what sorts might still escape. UNIONS 1 is especially helpful because it sits so close to the point where detection becomes a question of individual stellar membership. There may be no smooth galactic image to analyse. Instead, the galaxy search begins to resemble stellar archaeology. Astronomers identify a few old stars, compare their chemical fingerprints, measure their motions, and reconstruct the presence of a shared system. The galaxy, if it is a galaxy, is inferred through relationships rather than seen as a glowing whole. You might wonder how many stars are required before such a search becomes impossible. There is no fixed answer. A nearby system with a distinctive population may be identified with very few bright members. A more distant one could remain invisible even if it contains many more stars, because only its brightest giants rise above the detection limit. An ancient population may also lack luminous young blue stars and glowing gas, removing the features that make active dwarf galaxies easier to notice. UNIONS. One contains old, metal-poor stars and no known reservoir of gas producing new ones. There are no brilliant stellar nurseries, no supernovae lighting up clouds, and no young, massive stars acting as signposts. Its detectable population is the quiet residue of an early period of star formation. For most of cosmic history, it has apparently done very little that would attract attention. From the perspective of an astronomical survey, it is the neighbour who has lived nearby for years, never plays loud music, and is finally noticed only because someone carefully checks the records. That faint trail from survey images to confirmed stellar motions began with a task that sounds almost impossible. Search a large part of the northern sky for groups of stars that might be galaxies, even when those groups are too dim to look like galaxies at all. Astronomers could not rely on a bright centre, a visible outline, or a cloud of blended starlight. They had to search for a slight and unusual gathering of individual stars, then determine whether those stars truly belonged together or had merely appeared close to one another by chance. The first clues came from the Ultraviolet Near-Infrared Optical Northern Survey, usually shortened to UNIONS. The name describes a large imaging project that combines observations from several powerful telescopes to map a broad region of the northern sky at optical and near-infrared wavelengths. Part of its foundation came from the Canada-France Imaging Survey, carried out with the 3.6-metre Canada-France-Hawaii telescope on Mauna Kea. Its wide-field megacam instrument can photograph an area of about 1 square degree at a time, roughly 4 times the apparent area of the full moon, while recording hundreds of millions of pixels in each image. The survey was designed to cover thousands of square degrees with enough depth and image quality to detect very faint sources. A survey of that scale does not involve an astronomer looking at every image with a magnifying glass and circling anything suspicious. That might be a pleasant way to spend 1 or 2 evenings, perhaps with a large pot of tea, but it would become less charming after the first few million stars. Instead, the images are processed into catalogues. Software identifies individual sources, measures their positions, estimates how bright they are through different filters, and tries to decide whether each source is a star, a distant galaxy, an image defect, or something more troublesome that has arrived specifically to make the data reduction team sigh. Once the catalogue exists, astronomers can search it for patterns that would be almost impossible to notice in a normal photograph. Ursa Major 3/UNIONS 1 was found as a spatial overdensity of stars. That means a small area of sky appeared to contain more stars of a certain expected type than the surrounding region. The excess was not necessarily impressive when viewed casually. It became significant only after the stars were filtered according to the colours and brightnesses expected for an old, metal-poor population at a shared distance. This method is often described as a matched filter search. The basic idea is sensible. Suppose you're trying to hear a particular quiet note in a noisy room. Rather than treating every sound equally, you listen specifically for the pitch and pattern you expect. In a stellar survey, astronomers do something similar with light. They construct a model describing how the stars of a possible ancient satellite should appear in a colour magnitude diagram, then give greater weight to stars that lie near that model. A colour magnitude diagram compares a star's apparent brightness with its colour. The colour is measured by comparing how bright the star appears through different filters, and it acts as a rough indicator of surface temperature. Hotter stars generally appear bluer, while cooler stars appear redder. Brightness and colour together can reveal where a star sits in its life cycle. When many stars formed at approximately the same time from similar material, they arrange themselves along a recognisable path in this diagram. That path is not a picture of where the stars are located in space. It is closer to a family record of stellar development. Low-mass stars remain on the main sequence for very long periods. More massive members evolve away from it, pass through a turn-off point, and may become subgiants or red giants. The precise arrangement depends on age and chemical composition. An ancient metal-poor population has a different pattern from a young metal-rich one, even when the stars are mixed across the same patch of sky. Astronomers can use a theoretical curve called an isochrone to represent stars of one age and chemical composition. They shift that curve to different possible distances and ask whether any region of the survey contains an unusual number of stars lying close to it. The word isochrone sounds as though it might be a machine that politely tells time in several dimensions, but it simply means a line connecting stars of equal age in a model population. For UNIONS 1, the successful model pointed toward a population older than 11 billion years and very poor in heavy elements. Its estimated iron abundance was initially around 1/200th of the Sun's, expressed by astronomers as an iron to hydrogen value near -2.2 on a logarithmic scale. The pattern also suggested that the system lay roughly 10 kiloparsecs from the Sun, or about 33,000 light-years away. That is well within the broad domain of the Milky Way, but far enough that the ordinary stars in such a tiny system appear faint and difficult to measure. Finding the overdensity was still not enough. Any search covering thousands of square degrees will produce apparent clumps. The Milky Way itself is uneven. Dust changes the colours of stars. Streams and remnants of old systems cross the halo. The number of faint objects detected can vary with observing conditions. Some distant galaxies are compact enough to resemble stars. A few unrelated stars may also line up with the chosen isochrone through coincidence, especially when an algorithm tests many distances, ages and positions. The researchers therefore had to ask whether the candidate behaved like one physical object. Its stars should not merely occupy the same area of sky. They should share compatible distances, motions, and chemical properties. A genuine satellite should also show a spatial concentration, with the probability of membership generally increasing toward a common centre. By fitting the distribution of likely members, the Discovery team estimated a half-light radius of approximately 3 parsecs. A parsec is about 3.26 light-years, so half of the system's light appeared to come from within a radius of roughly 10 light-years. That is astonishingly compact for something proposed as a galaxy. It is much closer in size to a star cluster, although size alone cannot settle the classification. Its total luminosity was estimated at only about 11 times that of the Sun, corresponding to an absolute visual magnitude of approximately plus 2.2. The inferred mass in visible stars was initially just 16 solar masses, with considerable uncertainty because the population was so sparse. At this stage, the team had something interesting but fragile, a candidate built from photometry, meaning measurements of positions, brightnesses, and colours. The next task was to obtain kinematics, the actual motions of the stars. A few stars can appear to match the same ancient population while travelling through space in entirely different directions. If they belong to one bound object, however, their movements should cluster around a common value. The European Space Agency's Gaia mission provided part of this information. Gaia repeatedly measured the positions of nearly 2 billion objects, allowing astronomers to determine tiny changes in stellar locations over time. This movement across the sky is known as proper motion. It is not the speed of a star toward or away from us, but the sideways component of its apparent travel against the distant background. Combining proper motion with distance and radial velocity can reveal a star's three-dimensional motion through the Milky Way. Proper motion is normally far too small to notice by eye. The constellations seem permanent because human lifetimes are brief, compared with the time required for most stars to change their apparent positions substantially. Gaia measures those changes with extraordinary precision. In the case of UNIONS 1, 8 of the 11 original stars later identified as radial velocity members also had full Gaia astrometric measurements. Their proper motions were consistent with one another, supporting the conclusion that they formed a co-moving group rather than a random collection of foreground and background stars. Gaia could not complete the investigation alone. These stars are faint, and the most decisive test required spectroscopy from a much larger ground-based telescope. The astronomers turned to the W.M. Keck Observatory on Mauna Kea, where 2 telescopes each have a primary mirror 10 meters across. They used the Keck 2 telescope with the Deep Imaging Multi-Object Spectrograph, or DIMOS. This instrument can collect spectra from many targets during the same observation by using a carefully designed mask containing narrow slits aligned with selected objects. Imagine placing a metal sheet over a crowded view of the sky and cutting a tiny opening exactly where each chosen star will appear. Light from those stars passes through the slits, while much of the surrounding light is blocked. Inside the spectrograph, the light is spread into its component wavelengths, producing a spectrum for each target. Instead of receiving one small point of brightness, astronomers obtain a row of information showing how much light arrives at different wavelengths. A stellar spectrum contains dark absorption lines created when atoms in the star's atmosphere remove light at particular wavelengths. These lines act as markers. If a star is moving toward Earth, the entire pattern shifts slightly toward shorter wavelengths. If it is moving away, the pattern shifts toward longer wavelengths. This is the Doppler effect, the same basic principle that changes the apparent pitch of a passing siren, although stars are usually more considerate about the volume. By measuring these wavelength shifts, astronomers calculate radial velocity, the component of motion along our line of sight. Stars in a bound system do not all have exactly the same velocity. They orbit within the shared gravitational potential, so some move slightly toward us and others slightly away. Their measurements should nevertheless gather around a common systemic velocity. Foreground stars belonging to unrelated parts of the Milky Way are more likely to show different speeds. The first Keck observations identified 11 stars with radial velocities consistent with membership in UNIONS 1. When these results were combined with the Gaia proper motions and the photometric evidence, the case for a real stellar system became strong. The stars occupied the same small region, matched an ancient and metal-poor sequence, moved similarly across the sky, and shared a common motion along our line of sight. The object had been confirmed as a genuine Milky Way satellite, even though the question of whether it was a galaxy or a cluster remained open. That confirmation was a major achievement, because the original visual signal was so slight. Astronomers had moved from a small statistical excess in a survey catalogue to a physically associated system. Each stage removed a different kind of possible mistake. Colour and brightness rejected many stars of the wrong population. Spatial concentration rejected a broadly distributed background. Gaia proper motions tested whether the stars travelled together across the sky. Keck radial velocities tested whether they also shared motion toward or away from Earth. The velocity measurements then produced an unexpected result. The 11 original members appeared to have an intrinsic velocity dispersion of about 3.7 km per second. Velocity dispersion describes how widely the individual speeds are distributed around the system's average. For a system containing so little visible stellar mass, a spread of several kilometers per second seemed far too large. The gravity of 16 suns distributed across several parsecs should not drive stars at those relative speeds. If the value represented the object's equilibrium motion, a large amount of unseen mass would be required to hold it together. Dark matter became the obvious explanation. A tiny visible population could be sitting at the centre of a much more massive invisible halo. On paper, the ratio of total dynamical mass to visible light became enormous, potentially making UNIONS one of the most dark matter-dominated systems known. Yet the Discovery team immediately warned that the result was delicate. Removing the largest velocity outlier reduced the inferred dispersion from about 3.7 to about 1.9 km per second. Removing another influential star made the dispersion unresolved, meaning the remaining data could no longer establish a measurable internal spread. When one or two objects can alter the conclusion so dramatically, caution is not merely polite, it is required. A likely source of trouble was binary stars. Many points of light that look like single stars are actually pairs orbiting a shared centre of mass. During that orbit, one star may move toward Earth and then away from it. A spectrum taken on one night records that temporary orbital speed, in addition to the motion of the pair through the satellite. If astronomers assume the measurement represents the system's gravity, they can infer a velocity dispersion that is too large. This is particularly dangerous in an object with only 11 measured members. Suppose one star is moving unusually quickly because an unseen companion has pulled it toward us at the moment of observation. In a large galaxy with thousands of velocities, that one measurement would have little influence. In UNIONS 1, it could become the most important star in the calculation. It would be a little like estimating the average walking speed of a town by measuring 11 residents, one of whom happens to be sprinting after a bus. The discovery was therefore not the end of the observational work. It created a new list of questions. Were the outliers binary stars? Would their radial velocities change when measured again? Was the large dispersion real? Did the system contain dark matter, or could ordinary stars and faint stellar remnants explain it? Did its stars show a spread in chemical composition, which might indicate that the object had once retained gas and formed more than one generation? Answering these questions required multi-epoch spectroscopy, meaning repeated measurements separated in time. A star whose unusual speed comes from the shared motion of a dark matter-dominated system should remain broadly consistent from one observation to another, apart from measurement uncertainty. A binary star may show a changing radial velocity as it moves around its companion. One observation gives a snapshot. Several observations begin to reveal the orbit. The later campaign returned to UNIONS, one with deeper and more precise Keck data. In April 2025, researchers observed it again with Deimos for approximately 4.66 hours, using a new multi-slit mask designed to include previously confirmed members and additional faint candidates from the UNIONS catalogues. They successfully re-observed 10 of the original 11 stars and added 5 more members. Other facilities and instruments contributed additional epochs for selected targets, allowing the team to test for velocity changes. One original member was confirmed as a binary, and several others became binary candidates. The new measurements also showed that many stellar velocities moved closer to the system's average when observed with higher precision. This reduced the evidence for the original large velocity dispersion. The 2025 analysis, published in revised form in late 2025 and discussed in 2026, concluded that there was no longer positive observational evidence requiring dark matter. The researchers also measured metallicities for 12 members and found no large internal metallicity spread, making a star cluster classification more likely, though a dwarf galaxy was not completely ruled out. This later result does not undo the discovery. UNIONS. One remains a real and extraordinary stellar satellite. What changed was the interpretation of the force holding it together. The process shows why astronomical discovery is often gradual. An object can be detected first, confirmed second, characterized third, and reclassified later. Each step requires different observations, and each observation has its own limitations. There was no single evening when every secret of Ursa Major 3 became clear. Its discovery was assembled from survey exposures, source catalogues, colour measurements, theoretical stellar tracks, statistical maps, Gaia astrometry, Keck spectra, and repeated observations. The faint object gradually became more definite as independent pieces agreed. At the same time, its proposed identity became less definite as better measurements exposed the weaknesses of the first dynamical estimate. That combination is not unusual at the edge of astronomical knowledge. The existence of an object may become certain before its nature does. We know that these stars travel together. We know that they form an ancient, compact, extremely faint system. We know approximately where it is, how large it appears, and how little light it emits. What remains uncertain is whether the system began as a tiny galaxy inside a dark matter halo, or as a star cluster that has lost most of its visible members during a long interaction with the Milky Way. The naming reflects that unresolved history. UNIONS 1 honours the survey in which the overdensity was found, and leaves the classification relatively neutral. Ursa Major 3 places it among the known Milky Way satellites in the direction of the Great Bear and sounds more like the name of a dwarf galaxy. Astronomers often write both because neither label tells the complete story by itself. It is also worth noticing how much equipment was required to confirm so little visible material. A wide survey mapped thousands of square degrees. A space observatory measured minute changes in stellar positions. A 10-meter telescope collected faint spectra for hours. Sophisticated software compared observations with models and calculated membership probabilities. All of that effort was directed toward a system whose combined light is only several times greater than the Sun's. That imbalance is part of the appeal. Large objects are not always the most difficult to understand. A bright galaxy may offer millions of measurable stars, glowing gas, obvious structure, and a clear centre. UNIONS 1 offers almost none of those conveniences. Its small population turns every candidate member into an important witness. A single binary can confuse the dynamical result. A single bright giant can alter the estimated luminosity. A handful of chemical measurements can influence whether the system is called a galaxy or a cluster. The survey algorithms found the group because its stars followed the pattern of one old population. Gaia strengthened the case because several of them moved together across the sky. Keck confirmed their shared radial velocity, and then, with later observations, revealed that some of the first apparent motion may have come from binary companions rather than dark matter. The object became visible not through one dramatic image, but through agreement among several quiet measurements. Once astronomers had followed the faint signal through survey images, Gaia motions and Keck spectra, they were left with an object whose scale was almost difficult to accept. Ursa Major 3/Unions 1 was not simply small compared with the Milky Way. Every satellite galaxy is small compared with the Milky Way. This system was small compared with the objects that astronomers would normally hesitate to call galaxies at all. Its central region could fit within a modest stellar neighbourhood, its total light was weaker than that of some individual stars, and the population visible to our surveys could be discussed in numbers more suitable for a family gathering than for a galaxy. The phrase, about 60 stars, is often used to help describe Unions 1, although it should not be treated as a precise inventory in which every star has been counted and issued a little membership card. The actual number depends on what we mean by a star in the system, how faint an object our telescopes can detect, how many probable members are accepted, and whether we include invisible stellar remains. The original spectroscopy confirmed 11 stars through their radial velocities. Later observations expanded the secure member sample to 16. Beyond those confirmed targets, population models suggest that additional low-mass stars should exist below or near the detection limits of the surveys. The idea of roughly 60 stars is therefore best understood as an accessible estimate of the visible population, not a final census. Even with that caution, we're still talking about remarkably few stars. The Milky Way contains hundreds of billions. A typical globular cluster can contain hundreds of thousands. Even an open cluster that looks modest in a telescope may contain hundreds or thousands of members. Unions 1 may have only several dozen surviving visible stars bright enough to contribute significantly to its observed population, along with an uncertain collection of very faint stars, binary companions, white dwarfs, neutron stars, and perhaps stellar mass black holes. It is less like a miniature version of the Milky Way, and more like the final occupied corner of a structure whose original contents have mostly vanished. The visible stars do not all produce the same amount of light. One brighter, evolved star can contribute a large fraction of the luminosity, while many low-mass stars contribute very little individually. This is important because astronomers estimate the system's total brightness by modelling a stellar population from a limited sample. If one comparatively bright member is included or excluded, the estimated luminosity can change noticeably. In a large galaxy, one star has essentially no effect on the combined light. In Unions 1, a single star may influence the published properties of the entire system. The Discovery team estimated an absolute visual magnitude of about plus 2.2 and a total luminosity of approximately 11 times that of the Sun. Absolute magnitude describes how bright an object would appear if it were placed at a standard distance of 10 parsecs, or around 33 light-years. On this scale, lower and more negative values mean great brightness. The Sun has an absolute visual magnitude of roughly plus 4.8, so Unions 1 is brighter than the Sun, but not by anything resembling the margin expected from a galaxy. Its entire visible population emits only about 11 suns worth of light. There are individual stars in our part of the Milky Way that outshine this whole possible galaxy. Some familiar stars produce dozens, hundreds, or thousands of times the Sun's luminosity. A massive blue star can release more energy in a brief part of its life than Unions 1's remaining visible population produces collectively. If the system were compressed into one point and placed nearby, it would not appear as a grand galactic beacon. It would look like a reasonably bright star, and not even the sort of star that would make professional astronomers spill their tea. Of course, the light is not compressed into a point. It is distributed across a region several light-years wide. This makes the system even harder to see because its already weak luminosity is spread out. A bright point source stands out against the sky. The same amount of light divided among dozens of faint points can become difficult to recognize as one object. Each member looks like an ordinary Milky Way star, and only careful measurements reveal that the stars form a shared system. The measured half-light radius is about 3 parsecs, with an uncertainty of roughly 1 parsec. 3 parsecs is close to 10 light-years. The half-light radius is not the outer edge. It is the projected distance from the centre containing half of the measured light. Some probable members lie farther out, and the exact shape of the system remains uncertain because the sample is small. Still, this number gives us a useful sense of scale. Half of everything we can see from UNIONS 1 is concentrated within an area that light could cross in about 20 years from one side to the other. 20 years may sound like a long time when measured against a human life, but it is a very small diameter for a galactic system. Light needs around 100,000 years to cross the disk of the Milky Way. It takes more than 2 million years to travel from the Andromeda Galaxy to Earth. Within UNIONS 1's central region, light could leave one side during a child's first year and reach the other before that person had travelled very far into adulthood. If you could place the Sun at the centre of a sphere with a radius of 10 light-years, that sphere would contain our immediate stellar neighbourhood. It would include several nearby systems, some single stars, some binaries, and some faint red dwarfs that cannot be seen without telescopes. We would still describe it as one tiny patch within the Milky Way. UNIONS. One gathers much of its visible light into a region of comparable scale, although the total object extends beyond its half-light radius. A candidate galaxy is therefore occupying a space we normally think of as a local neighbourhood inside a galaxy. The stars themselves are not crowded in the way they are near the centre of a dense globular cluster. A radius of 3 parsecs sounds compact for a galaxy, but it can still leave considerable distances between several dozen stars. If 60 visible members were spread evenly across a sphere of that size, the average separation would remain large enough that each star would have a wide region of darkness around it. The actual distribution is not perfectly even, and the half-light radius is a projected measurement rather than a simple, 3-dimensional boundary, but the general picture holds. UNIONS 1 is tiny without necessarily being packed. Standing near one of its stars, assuming such a visit were possible, and the star had somewhere sensible to stand, would not reveal a sky filled with nearby suns. Most of the other members would still appear as points separated by blackness. There would be no bright band resembling the Milky Way as seen from Earth, because there are not enough stars to create one. The system might feel less like living inside a galaxy, and more like occupying a very sparse group whose connection could be recognised only by measuring motion over long periods. Our own night sky appears rich because we are embedded in the disk of the Milky Way. Even when most stars are too faint to see individually, their combined light forms a pale band. Gas clouds glow. Dust blocks more distant starlight and produces dark lanes. UNIONS. One has no known spiral arms, no large clouds of star-forming gas, no bright nebulae, and no young stellar population. Its known stars are old and quiet. The most massive stars that once belonged to the original population completed their lives billions of years ago. This is where the description of 60 ancient stars becomes more complicated. The objects visible today are not necessarily all that remains physically. They are what remains luminous enough for us to notice. An old population begins with stars covering a range of masses. The most massive consume their nuclear fuel quickly and may survive for only millions of years. Stars somewhat more massive than the Sun last longer, but still finish their active lives well before 11 billion years have passed. Only the lowest mass stars can remain on the main sequence for the full age inferred for UNIONS 1. Any massive stars originally born there would already have evolved. Some may have exploded as supernovae, leaving neutron stars or black holes. Others would have shed their outer layers more gently and become white dwarfs. Many remnants may have escaped the system, especially if they received strong kicks during stellar death. Others could have remained and now contribute mass without contributing much detectable light. In simulations treating UNIONS 1 as an old star cluster, compact remnants can account for a large fraction of the present-day mass, while remaining effectively invisible to the surveys that discovered the luminous stars. That possibility changes the mental image. Instead of picturing 60 stars and nothing else, imagine several dozen faint lamps moving through a small dark structure that may also contain the cooled cores of dead stars. White dwarfs would be extremely dim at this distance. Neutron stars might emit little detectable radiation, unless they were active pulsars or accreting matter. Stellar mass black holes would produce no light of their own. The system could therefore contain more objects and more mass than its visible membership suggests. Binary systems add another hidden layer. A point that appears to be one star may consist of two stars orbiting each other too closely to be separated in the image. Spectroscopic measurements can reveal some binaries because their radial velocities change as the stars orbit, but very long period or unfavourably aligned systems may remain difficult to identify. The later study of UNIONS, one confirmed at least one velocity variable binary and found other possible candidates. One reason the original estimate of a large velocity dispersion became less convincing. When people hear that a system contains around 60 stars, it is natural to imagine that astronomers have viewed all 60 directly. In reality, faint stellar populations are reconstructed statistically. A survey detects stars above a certain brightness. Astronomers compare those detections with theoretical models of how many lower mass stars should exist. They also account for stars that may fall outside the chosen search radius, stars that overlap with foreground contamination, and members too faint to distinguish from noise. A very low-mass red dwarf can shine for trillions of years, but its light is weak. At a distance of about 33,000 light-years, such a star may be beyond the completeness limit of the survey. A somewhat brighter star can be detected, yet obtaining a useful spectrum may require hours on a 10-metre telescope. The 16 spectroscopically confirmed members are not the only possible residents. They are the members from which astronomers have obtained the strongest evidence. This is why star counts and stellar mass are related but not interchangeable. The original estimate placed the total mass in stars at roughly 16 solar masses, with uncertainty extending several solar masses in either direction. A population of 60 stars could fit within such a mass if most were low-mass objects. Many ancient surviving stars may contain only a fraction of the Sun's mass. A group of low-mass red dwarfs can include a surprisingly large number of members while adding up to relatively little total mass. Stellar mass estimates are also affected by assumptions about the initial mass function, the distribution of stellar masses when the population formed. Astronomers cannot directly observe the original high-mass stars because they are gone. They use models to infer how many stars of different masses were likely born, and how that population changed through stellar evolution, binary interaction, and tidal stripping. A different assumed history can produce a different estimate of the number of surviving stars and remnants. If UNIONS 1 is a dwarf galaxy, its visible stars may be the tiny luminous population that formed inside a dark matter halo and then stopped forming stars very early. In that interpretation, the small number of stars does not represent the full gravitational system. The visible population would be a tracer, rather like a handful of leaves floating on an invisible current. The dark matter halo could be many times larger than the stellar distribution, and would contain almost all the mass. If the object is a star cluster, the story changes. It may have begun with thousands of stars and gradually lost most of them to the Milky Way's tides, and to internal dynamical evolution. Simulations have explored progenitors containing several thousand stars, evolving for about 12 billion years until only a few dozen members remained visible within the range accessible to surveys like UNIONS. In those models, low-mass stars escape preferentially, while heavier remnants drift inward through mass segregation and help keep the remaining cluster bound. Mass segregation is a slow rearrangement caused by repeated gravitational encounters. Stars do not collide directly in most clusters, but they pass near one another and exchange small amounts of energy. Over long periods, heavier objects tend to settle toward the centre, while lighter stars move to wider orbits and are more easily stripped away. it is not a perfectly organised process. No star receives a polite notice informing it that it has been reassigned to the outskirts. The result emerges from countless weak interactions. In a system as old as UNIONS 1, there has been plenty of time for such evolution. If it began as a cluster, the population we observe now may be strongly altered from the population at birth. The present stars would not simply be an untouched sample of the original group. They would be the survivors that happen to have the right masses, positions and velocities to remain after billions of years of stellar deaths and gravitational losses. That is one reason the small number is scientifically useful. A nearly dissolved cluster carries evidence of how stellar systems lose members. Its mass function, meaning the number of stars found in different mass ranges, should become depleted at the low mass end because lightweight stars escape more easily. A dwarf galaxy protected by dark matter may retain a stellar mass distribution closer to the one it formed with. Deeper observations that count very faint low-mass stars could therefore help distinguish between the two identities. The system's chemistry offers another clue. The original discovery analysis described the population as extremely metal-poor, with an estimated iron abundance around 1/200th of the solar level. Later, spectroscopy measured 12 members and found a mean iron abundance of about -2.65 on the logarithmic scale used by astronomers. This corresponds to an iron content only a few hundredths of 1% of the Sun's value, depending on the exact comparison and calibration. The later study found no large metallicity spread, which currently favours a star cluster, although the sample and measurement precision do not eliminate every dwarf galaxy possibility. A metallicity spread would mean that different stars contained noticeably different amounts of heavy elements. In a dwarf galaxy, a dark matter halo can create enough gravity to retain some gas expelled by supernova. New stars may then form from material enriched by earlier generations, producing a range of chemical compositions. A small star cluster often forms its stars over a shorter period and cannot retain supernova ejecta efficiently, leaving a more uniform population. UNIONS 1 appears to contain only one known red giant among its confirmed members, with the rest mainly consisting of stars near the main sequence. Red giants are valuable because their brightness makes them easier to study spectroscopically, but having only one creates obvious limits. Astronomers cannot build a detailed chemical history from a single bright evolved star. They must gather light from much fainter main sequence members, which is technically demanding even with observatories such as Keck. Each faint spectrum represents hours of collected photons from a star that may be older than the Sun by 6 or 7 billion years. The light leaves the star, travels across roughly 33,000 light-years, passes through Earth's atmosphere, enters a slit cut for that exact target, and is divided into wavelengths. From small dark lines in that spectrum, researchers estimate velocity and chemical composition. The number of photons may be modest, but the information hidden within them can determine whether the system is classified as a galaxy. There is an appealing mismatch between the smallness of the object and the size of the questions attached to it. A few dozen ancient stars can test theories of dark matter. Their chemical similarity can reveal whether the system retained gas. Their mass distribution can show whether the Milky Way stripped away lighter members. Their orbital speeds can distinguish between a dark halo and a cluster supported by ordinary stellar remnants. Very few stars are being asked to provide a great deal of evidence. Still, their age may be the most important shared feature. These are not stars that gathered recently. The best-fitting stellar population is older than 11 billion years, making it more than twice the age of the Sun. Whatever UNIONS 1 is today, its visible members formed when the universe was only a few billion years old. They have remained associated, or at least recognizably associated, through most of cosmic history. During those billions of years, the system has orbited within the growing gravitational environment of the Milky Way. The galaxy around it changed. Other satellites arrived and were destroyed. The disk accumulated stars and gas. Spiral structure developed and shifted. The central regions grew. UNIONS 1 continued along an orbit that repeatedly exposed it to the Milky Way's tidal pull. A collection with only a few dozen visible survivors should appear temporary, yet the population is ancient. That tension sits at the heart of the mystery. How can something apparently so fragile have remained recognizable for more than 11 billion years? Was it protected inside a dense halo of dark matter? Did it begin as a much larger cluster and lose nearly everything? Are unseen remnants now supplying more binding mass than its light suggests? Or are we observing it during the final stage of a very long dissolution? Long before the Sun existed, before Earth had oceans, and before the Milky Way had settled into the familiar form we see today, the stars of Ursa Major 3/UNIONS 1 were already shining. Their exact formation date cannot be read from a tiny label attached to the system, unfortunately, but the colours and brightnesses of its members fit a population older than 11 billion years. That places their birth in a period when the universe was only a few billion years old and our galaxy was still assembling from smaller structures, gas clouds, dark matter, and repeated mergers. The system we observe now may contain only a few dozen visible survivors, yet those stars belong to an era so early that almost everything around them has changed. It is useful to pause over what that age really means. The universe is about 13.8 billion years old. A stellar population older than 11 billion years therefore formed during roughly the first fifth of cosmic history. At that time, many galaxies were smaller and less organised than they are today. The Milky Way had not yet completed the broad disk, spiral arms, and extended population of stars we now call home. It was growing through the collapse of gas and the absorption of smaller systems, rather like a city being built while several nearby towns are quietly incorporated into it, except with fewer planning meetings and considerably more gravity. The stars of UNIONS 1 are not all 11 billion years old precisely the same afternoon. Astronomers estimate age by comparing their observed colours and luminosities with models of stellar evolution. A group of stars formed at approximately the same time follows a predictable pattern as its members age. The most massive stars burn through their fuel quickly and disappear from the main sequence first. Lower mass stars remain stable much longer. The point where stars begin leaving the main sequence, known as the main sequence turnoff, is especially useful because its position changes with the age of the population. In a very old system, the turnoff occurs among relatively low-mass stars. The brighter, hotter stars that would have occupied the upper main sequence are long gone. Their lives ended billions of years ago, leaving white dwarfs, neutron stars, black holes, or material that escaped entirely. What remains visible is dominated by lower mass stars that consume hydrogen slowly. They are the careful spenders of the stellar world, stretching their fuel across time spans that make the Sun's present age seem almost youthful. Astronomers also examine the abundance of heavy elements in these stars. In astronomy, elements heavier than hydrogen and helium are broadly called metals, a definition that would make a chemist raise an eyebrow, but is now too deeply established to change without paperwork. The stars of UNIONS 1 are extremely metal poor. The Discovery analysis estimated an iron abundance around -2.2 on the logarithmic scale used by astronomers, while later spectroscopy of 12 members found a mean value near -2.65. This means their material contained far less iron than the Sun, consistent with formation before many generations of stars had enriched the universe. Hydrogen and helium were produced in enormous quantities during the earliest stages of the universe. Most heavier elements came later. Stars fused lighter nuclei into heavier ones, and stellar death spread some of those products into surrounding space. Carbon, oxygen, silicon, calcium and iron gradually accumulated as one generation followed another. A young star forming today in the Milky Way is born from gas that has been processed through many earlier stars. An ancient metal-poor star formed from material that had experienced far less enrichment. The chemistry of UNIONS 1 therefore acts as a rough historical marker. Its stars appear to come from an environment where only a limited number of previous stellar generations had contributed heavy elements. They are not completely free of metals, so they were probably not among the very first stars in the universe. Those hypothetical first stars formed almost entirely from hydrogen and helium, and are expected to have been massive and short-lived. The members of UNIONS one came somewhat later, after at least some enrichment had occurred, but still early enough to preserve a chemical record that is now rare. Whether the system formed inside the young Milky Way, or arrived later as part of another structure is not yet known. The stellar age tells us when the stars formed, but it does not automatically tell us where they formed, or whether they have remained bound in exactly the same object ever since. A small cluster could have been born in a larger dwarf galaxy and later stripped away. A tiny dwarf galaxy could have fallen into the Milky Way independently. The present system may also be the remnant of something that once contained far more stars. This distinction is important because the phrase 11 billion-year-old survivor can create the impression that UNIONS one has spent 11 billion years in its current form, making the same orbit at the same size with the same few dozen members. Nature is rarely that tidy. The Milky Way's mass has changed. Its gravitational field has evolved. Satellite orbits can be altered by interactions, and stellar systems lose mass over time. UNIONS one may be ancient, but the faint remnant visible today could be the result of a very long transformation. Even so, the stars themselves have remained recognizable as a shared population. They move together through the Milky Way's halo on an inclined orbit, rather than circling neatly within the galactic disk. Models based on its position, distance, radial velocity, and Gaia proper motion place the closest point of its current orbit at roughly 13 kiloparsecs from the galactic centre and the farthest point near 30 kiloparsecs. One full radial cycle, travelling from a close approach outward and then returning, takes roughly 400 million years in the models used for the early dynamical studies. A kiloparsec is 1,000 parsecs, and 1 parsec is about 3.26 light years. A distance of 13 kiloparsecs is therefore approximately 42,000 light years from the centre of the Milky Way. 30 kiloparsecs is close to 98,000 light years. The orbit carries the system through the Galaxies' extended halo, beyond much of the bright stellar disk, but not so far away that the Milky Way's gravity becomes gentle or unimportant. The Sun sits roughly 26,000 light-years from the galactic centre. UNIONS one's present path brings it through a range of galactocentric distances that overlaps the broad outskirts of the visible galaxy and reaches well into the halo. It does not remain at a constant radius. Its orbit is elongated, so its speed and the strength of the surrounding tidal field change as it moves. Near the farthest point, called epicenter, it travels more slowly. Near the closest point, called pericenter, it moves faster and experiences a stronger gravitational influence from the Milky Way. This motion should not be imagined as a tiny object tracing a bright line around the galaxy, like a bead sliding along a wire. There is no visible orbital track. The system moves through a nearly empty-looking halo, and one journey takes hundreds of millions of years. During the entire recorded history of human civilization, UNIONS 1 has advanced through only a tiny fraction of one orbit. Even during the age of the dinosaurs, it completed only part of a cycle. If its present radial period had remained similar for 11 billion years, the system could have experienced several dozen close approaches to the inner Milky Way. The true number cannot be calculated by simply dividing its age by its current orbital period, because the galaxy and orbit evolved over time. Still, the comparison illustrates the problem. This is not an object making its first quiet pass through our neighbourhood. Its ancient stars have probably endured repeated episodes of stronger tidal stress. Tidal forces arise because gravity changes with distance. The side of UNIONS, one facing the Milky Way, is pulled slightly more strongly than the far side. For Earth, the same basic effect helps create ocean tides through the gravity of the Moon and Sun. Across a small stellar system, the consequences unfold over much longer periods. Stars on the outer edges can be nudged into wider orbits, and some eventually gain enough energy to escape. Near pericenter, the difference in gravitational pull becomes stronger. The Milky Way's disk, bulge, and dark matter halo all contribute to the surrounding potential. If UNIONS 1 crosses near or through denser regions, the changing gravitational field can shock the system, injecting energy into stellar motions. Repeated passages gradually weaken an object whose own gravity is not strong enough to hold every member. A massive dwarf galaxy can resist this process through its dark matter halo. A dense globular cluster can survive because its stars are tightly bound. UNIONS 1 appears to have neither an obvious large stellar mass nor a visibly dense population. Its half-light radius is about 3 parsecs, while its estimated visible stellar mass is only around 16 times that of the Sun. Taken at face value, those properties describe an object with extremely weak self-gravity. A system containing thousands or millions of solar masses can lose some stars without immediately dissolving. UNIONS 1 cannot afford many departures. If only several dozen visible stars remain, the loss of a few members represents a meaningful fraction of the population. One escaping star is not a rounding error. It is more like someone quietly removing a chair from a very small dinner party and hoping no one notices. The first simplified simulations treated UNIONS 1 as a self-gravitating stellar system without dark matter. In those models, an object with its measured mass and size could not survive for much longer than a single current orbit. It was disrupted within roughly 400 million years, or at most a few close passages depending on the exact assumptions. Because the stars appear older than 11 billion years, the result created an uncomfortable coincidence. Why would astronomers discover such an ancient system during the brief final stage of its destruction? One possible answer was that UNIONS 1 is not supported by its visible stars alone. A compact dark matter halo could provide the missing gravity, holding the stellar population together during repeated journeys around the Milky Way. That interpretation became one of the strongest early arguments for calling the object a galaxy. A star cluster is ordinarily bound mainly by the mass of its stars and stellar remnants. A galaxy is expected to sit inside a dark matter halo. Another possibility was that the original simulations simplified the internal life of such a small system too much. A cluster containing a limited number of stars is collisional in the astronomical sense. This does not mean stars frequently crash into each other. They pass close enough for their gravitational interactions to exchange energy, gradually reshaping the system. Binary stars, mass segregation, stellar evolution, and compact remnants can all affect how long the cluster survives. Later collisional simulations included these effects in more detail. Some models began with a more massive star cluster and allowed it to evolve for about 12 billion years under the Milky Way's tidal influence. Low-mass stars were preferentially lost, while heavier remnants such as white dwarfs, neutron stars and stellar mass black holes became more centrally concentrated. The models could produce a faint present-day remnant resembling UNIONS 1 without requiring a dark matter halo, and they estimated that such a cluster might still survive for another 2.7 billion years. These newer simulations do not prove that UNIONS 1 is a star cluster. They demonstrate that long survival may be possible under assumptions that were not included in the earlier simplified treatment. Scientific models are controlled experiments performed with equations and computers. Their conclusions depend on the ingredients placed inside them. Add realistic stellar evolution and retained remnants, and a cluster can remain heavier than its visible light suggests. Change the number of binaries or the initial mass distribution, and the result can shift again. The present system may therefore be the result of selective survival. Low-mass stars on wide orbits are relatively easy for the Milky Way to remove. More massive objects tend to sink toward the centre through mass segregation. Over billions of years, UNIONS 1 could lose much of its visible population while keeping a concentrated group of dark stellar remnants. Those remnants are made of ordinary matter, not dark matter, but they emit very little light. A white dwarf is the dense core left by a star similar to the Sun. It may begin hot but gradually cool and fade. A neutron star compresses more mass than the Sun into a sphere only tens of kilometers wide. A stellar mass black hole produces no light unless matter falls toward it. At a distance of roughly 33,000 light-years, a quiet collection of such objects would be extremely difficult to detect directly. Their gravity, however, would remain. A cluster containing only a few dozen visible stars could be held together partly by a hidden population of stellar remains. This would make its mass-to-light ratio unusually high without making it a dark matter-dominated galaxy. It is a useful reminder that darkness has more than one cause. An object can be dark because it contains exotic non-luminous matter, or because much of its ordinary matter has finished shining. The orbit may also produce visible clues through stars already removed from the system. Escaping members should not scatter randomly in every direction. They tend to form leading and trailing tidal tails roughly aligned with the orbit. Over time, these tails can become thin stellar streams extending far beyond the remaining core. Detecting such a stream around UNIONS, one would support the idea that the Milky Way is actively stripping it. Finding those stars would be extremely difficult. The central object is already barely detectable. A tidal tail would spread its few escaped members across a much larger region, lowering the density even further. Instead of searching for a faint needle in a haystack, astronomers would be searching for several pieces of the needle after the haystack had been moved across the garden. The stars in a stream should share related motions and chemical properties, allowing future surveys to distinguish them statistically from the surrounding halo. Deep imaging could identify candidates with the correct colours and brightnesses. Gaia or later astrometric missions might measure proper motions for the brighter members. Spectroscopy could then test whether they share the system's radial velocity and metallicity. No obvious large tidal structure has yet settled the matter. The current system is compact, and its visible shape does not provide a simple answer. An object can also be near disruption without displaying an easily detected stream, especially when the total number of stars is so low. Absence of visible tails is therefore not strong proof that no stripping has occurred. Another clue may come from its orbit's orientation and history. Satellite systems do not always arrive independently. Some enter the Milky Way as members of groups, orbiting a larger dwarf galaxy before the entire group is captured. Others may be related to ancient merger events whose remains now form structures in the stellar halo. Reconstructing these associations requires comparing positions, motions, orbital poles, and chemical patterns. For UNIONS 1, the available evidence describes an inclined halo-like orbit, but does not yet provide a secure birthplace. Its ancient metal-poor stars could have formed in a very small early halo. They could have belonged to a star cluster inside a now-destroyed dwarf galaxy. They may have been associated with a larger accretion event whose other remnants are scattered across the Milky Way. Each possibility would produce a different account of how the object reached its current path. Whatever the route, the Milky Way it first encountered was not the same galaxy it orbits today. More than 11 billion years ago, the galactic disk was less massive and less settled. The gravitational potential changed as stars, gas, and dark matter accumulated. Large merger events heated and rearranged older populations. The orbit of a small satellite would respond to this evolving environment. This makes any backward reconstruction uncertain. Astronomers can integrate the present orbit through a model of the current Milky Way, but extending that path billions of years into the past requires assumptions about the galaxy's earlier mass and interactions. Small changes accumulate. Encounters with other satellites, especially massive ones, can alter trajectories. The Large Magellanic Cloud, for example, affects orbit calculations for some Milky Way companions, because it is massive enough to perturb the surrounding gravitational field. The phrase orbiting the Milky Way therefore describes a continuing relationship rather than a perfectly repeated path. UNIONS. One belongs to the galactic halo and is gravitationally connected to our galaxy, but its exact route has probably changed. Like a leaf circling in a slowly shifting current, it follows the local pull, while the larger environment evolves around it. Its survival is also not necessarily all or nothing. A stellar system can remain recognizable while continuously losing mass. The core may stay bound as the outskirts are stripped. Its radius can change. Its internal distribution of stellar masses can become altered. A cluster that began with thousands of stars may eventually contain only dozens, while still preserving a common motion and center. This gradual reduction may explain why UNIONS 1 looks so extreme today. Perhaps it was not born as the smallest system. It became the smallest through time. Each pericentric passage removed some members. Internal encounters pushed low-mass stars outward. Massive stars evolved into dark remnants. After billions of years, very little visible material remained. If it began as a dwarf galaxy, the stellar history may have been different. A dark matter halo could have formed early, gathered a small amount of gas, and produced only a limited burst of stars before reionization or stellar feedback removed or heated the remaining gas. The stars then aged quietly, while the dark halo protected them. Tidal forces may have stripped much of the outer halo but left a dense central remnant. Reionization occurred when radiation from early stars and galaxies transformed much of the universe's neutral hydrogen into ionized gas. For very small dark matter halos, this heating made it harder to capture and cool gas. Some halos may have formed a few stars before reionization and then stopped almost permanently. Ultra-faint dwarf galaxies are often studied as possible fossils of this early period because they're old. Metal-poor populations contain evidence of star formation that ended very early. UNIONS 1 could represent an extreme version of such a fossil, but only if it is truly a galaxy. Its handful of stars would show that an early dark matter halo managed to cross the threshold for star formation, though only barely. It would have produced enough light for us to find it 11 billion years later, but not enough to resemble a normal galaxy in any familiar image. The later spectroscopic results have made that interpretation less certain. 16 members are now known dynamically, and the improved velocities strongly favour a much smaller intrinsic dispersion than the original estimate. The first metallicity measurements also reveal no large chemical spread. Those findings currently fit a star cluster more naturally, although they do not eliminate every dark matter scenario. Yet the age and orbit remain remarkable regardless of the label. If UNIONS 1 is a cluster, it is an extraordinarily faint and metal-poor remnant that has endured the Milky Way's tidal field for most of cosmic history. If it is a dwarf galaxy, it is an almost completely dark system that formed a tiny stellar population near the beginning of galaxy formation. In either case, the visible stars are survivors from an environment that no longer exists. They have watched nothing, of course. Stars do not remember in the human sense. Still, their present properties preserve consequences of earlier events. Their chemistry reflects the gas from which they formed. Their masses reflect which stars have lived long enough to remain luminous. Their arrangement reflects internal encounters and tidal losses. Their shared motion records their current journey around the Milky Way. By studying these few members, astronomers are trying to reconstruct an 11 billion year history from a very incomplete final page. The original population is uncertain. The number of lost stars is unknown. The content of compact remnants cannot yet be counted directly. Even the presence of dark matter remains unresolved. Every interpretation must explain how such a faint object can still exist after repeated exposure to the Milky Way. The few ancient stars of Ursa Major, 3/UNIONS 1, do not look as though they should possess enough gravity to remain together. Their combined visible mass is only a few tens of times greater than the mass of the Sun, and they are spread across a region several light-years wide. If those stars were all that existed, their mutual pull would be extremely weak. They should move slowly around one another, and the Milky Way should be able to disturb them with relative ease. Yet the first measurement suggested that the stars were moving far more quickly than their visible mass could explain. That unexpected motion raised an extraordinary possibility. Perhaps the little group of stars was only the illuminated centre of a much larger invisible object. That invisible material would be dark matter, the substance believed to provide most of the mass in galaxies while producing no light that telescopes can detect directly. Dark matter does not glow like a star, reflect light like a planet, or form bright clouds like ordinary gas. Astronomers infer its presence through gravity. They observe how visible objects move and ask whether the matter they can see is massive enough to produce those motions. When the answer is no, an unseen source of gravity may be required. This method has been used on scales far larger than UNIONS 1. Stars in the outer regions of spiral galaxies orbit too quickly to be held by the visible stars and gas alone. Galaxies inside clusters move as though the clusters contain much more mass than their luminous material provides. Gravitational lensing bends the light of distant objects more strongly than ordinary matter can account for. Across the universe, these observations point toward large amounts of invisible mass, arranged in halos around galaxies and clusters. UNIONS 1 presented the same basic question in a much smaller package. Instead of tracking billions of stars around a large galaxy, astronomers were measuring the radial velocities of only 11 likely members. Radial velocity tells us how quickly a star is moving toward or away from Earth. The stars in a gravitationally bound system should not all have exactly the same velocity because they are moving within the system, but their speed should cluster around a shared average. The width of that cluster of speeds is called the velocity dispersion. A cold system has a small dispersion, meaning its members move at similar velocities. A dynamically hot system has a larger one. The term hot does not refer to the surface temperatures of the stars. It describes the amount of random motion. A group of stars moving rapidly in different directions is dynamically hot, even if every member is a very cool red dwarf. The Discovery observations produced an estimated line-of-sight velocity dispersion of about 3.7 kilometers per second. That may not sound especially fast. A car on a motorway moves at a respectable fraction of a kilometer per second, and many stars travel through the Milky Way at hundreds of kilometers per second. The important comparison is not with cars or with the galactic orbit of the system. It is with the speed expected inside an object containing only around 16 suns of visible stellar mass. For such a light and compact group, a stellar-only internal dispersion was expected to be closer to 1/10 of a kilometer per second. The original value was therefore enormously larger than the visible stars seemed capable of producing. To understand why this points toward unseen mass, imagine placing a few lightweight objects in a loose group and watching them move rapidly around a shared centre. If their speeds are high and the group remains together, something must provide enough gravity to prevent them from escaping. The faster the members move, the more mass is generally needed to bind them. Without that mass, the group would disperse rather than continue behaving like one object. Astronomers estimate the dynamical mass of a stellar system by combining its size with its velocity dispersion. The exact formula depends on the shape of the system, how the stellar orbits are distributed, and whether the object is in equilibrium, but the basic relationship is simple. A larger velocity dispersion implies a greater mass. A larger size also requires more mass to hold stars moving at a given speed. For UNIONS 1, the original combination of a 3-parsec half-light radius and a dispersion near 3.7 kilometers per second implied a dynamical mass vastly greater than the mass of the visible stars. The corresponding mass-to-light ratio could rise into the thousands in solar units, meaning that for every amount of visible light equivalent to the sun's, the system might contain thousands of solar masses in total gravitating material. Ordinary star clusters usually have mass-to-light ratios much closer to a few because most of their mass is contained in stars and stellar remnants. A ratio in the thousands would place UNIONS 1 in the territory of an extremely dark matter-dominated dwarf galaxy. The phrase dark matter-dominated is especially important. Every ordinary galaxy contains stars, gas, and stellar remnants. But in the smallest dwarf galaxies, dark matter may outweigh all of that visible material by a very large factor. The stars behave almost like test particles tracing an invisible gravitational field. They reveal the halo's presence without contributing much to its total mass. If UNIONS 1 were such a system, the visible stars might represent only a tiny decorative feature inside a halo that originally contained millions or perhaps billions of solar masses. One early modelling study considered the possibility that the stars formed at the centre of a cuspy dark matter halo with an original mass of around 1 billion suns. The outer parts of that halo could later be stripped by the Milky Way, while the dense central region survived and continued protecting the stars. The predicted velocity dispersion in such a surviving central system was of the order of 1 kilometre per second, within the broad range allowed by the uncertain early observations. A dark matter halo would also help solve the survival problem. As we have seen, a tiny collection of ordinary stars travelling around the Milky Way should be vulnerable to tidal disruption. The galaxy pulls more strongly on the near side of the system than on the far side, gradually stretching it and removing members. Add a dense invisible halo, however, and the stars sit inside a much deeper gravitational well. They can survive repeated passages through the Milky Way's tidal field, even when their own stellar mass is almost negligible. This was one reason the dark matter interpretation initially seemed so persuasive. Two independent clues appeared to point in the same direction. The stellar velocities suggested more mass than could be seen, while early simulations suggested the dark matter-free cluster should dissolve within roughly one current orbit, around 400 million years. Since the stars themselves are older than 11 billion years, observing the cluster during such a brief final interval seemed unlikely. A durable dark halo offered a solution to both puzzles at once. The object quickly became interesting not only to researchers studying galaxies, but also to physicists searching for the nature of dark matter itself. Some hypothetical dark matter particles may occasionally collide or annihilate with one another, producing ordinary particles such as gamma rays. The expected signal depends strongly on how much dark matter is concentrated along our line of sight. A nearby compact dwarf galaxy with an unusually dense halo could become one of the most promising targets for indirect detection. Researchers examined 15 years of observations from the Fermi Gamma Ray Space Telescope in the direction of Ursa Major 3. They found no significant excess of gamma rays. Under the assumption that the original high dark matter density was correct, that non-detection could place very strong limits on certain dark matter annihilation models. The catch was substantial. The power of those limits depended on UNIONS 1 truly being a dark matter-dominated galaxy with the inferred density. If the stellar velocities had been misinterpreted, the expected dark matter signal would also have been overestimated. The entire case therefore rested on a small set of faint stars and on assumptions that work well for larger systems but become fragile at this scale. Velocity dispersion is not a direct reading from a single instrument. It is a statistical estimate. Astronomers measure the speed of each likely member, account for measurement uncertainties, and calculate how much intrinsic variation remains. With hundreds of stars, an unusual measurement has little influence. With 11, every star can change the answer. The original researchers were careful about this from the beginning. The largest velocity outlier had a major effect. When that star was removed, the estimated dispersion fell from about 3.7 to about 1.9 kilometers per second. Removing another outlier left the dispersion unresolved, meaning the data no longer required any measurable spread beyond the uncertainties. This did not prove that the outliers were wrong, but it showed that the dramatic dark matter result was being carried by a very small number of measurements. Binary stars offered the most obvious source of confusion. A star may appear as a single point while orbiting an unseen companion. During one part of the orbit it moves toward Earth, and during another part it moves away. The radial velocity measured on a particular night includes this orbital motion. If astronomers treat that temporary speed as movement through the larger system, the velocity dispersion can appear inflated. The problem is easy to picture with a small group. Suppose 11 people are walking together along a street. 10 are moving at almost the same pace, while one is jogging in a circle around a companion. If you record everyone's speed from a single angle and calculate the spread, the circular runner makes the whole group appear less orderly. The group itself may still be moving calmly. One member simply has an additional local motion. Binary contamination matters less in massive galaxies because their true velocity dispersions are large. A binary orbit adding a few kilometers per second is a minor disturbance, when the galaxy's stars already move with dispersions of tens or hundreds of kilometers per second. In UNIONS 1, the expected stellar-only dispersion is around 1/10 of a kilometer per second. Binary motion can be many times larger than the signal astronomers are trying to measure. Multi-epoch spectroscopy is the main defense. Instead of measuring each star once, astronomers observe it on several dates. A normal member moving through a steady gravitational potential should maintain roughly the same radial velocity. A binary may change as its orbital position changes. The pattern can be difficult to detect if the orbit is long or nearly face-on, but repeated measurements greatly reduce the danger of mistaking binary motion for dark matter. By 2025, new Keck observations had expanded the sample to 16 members and provided more precise velocities, including repeated measurements of many stars. At least one influential original member was found to be a spectroscopic binary, and other binary candidates were identified. The revised analysis placed a 95% confidence upper limit of 2.3 kilometers per second on the internal dispersion, but the most important result came from comparing different models. The new data favoured the expected stellar-only dispersion of roughly 0.1 kilometers per second over the original 3.7 kilometer per second value by a likelihood ratio of about 120 to 1. The authors concluded that there was no current observational evidence for dark matter in the system. That conclusion needs to be stated carefully. No observational evidence does not mean astronomers proved that UNIONS 1 contains no dark matter. The new measurements did not resolve a high dispersion, so they no longer require an invisible halo. A sufficiently modest dark matter contribution could still be present within the allowed range, and a dwarf galaxy interpretation was not completely excluded. The balance of evidence, however, moved toward a self-gravitating star cluster. The chemical measurement supported the same shift. A true dwarf galaxy may retain gas long enough for more than one generation of stars to form. Supernovae enrich the gas with heavy elements, producing a measurable spread in metallicity among later stars. A small star cluster usually forms most of its population over a shorter interval and cannot hold on to supernova ejecta, so its stars tend to have more uniform ion abundances. The follow-up study measured metallicities for 12 members and found an average ion abundance of about -2.65, confirming that the system is extremely metal poor. It placed an upper limit of 0.35 dex on any internal metallicity dispersion at 95% credibility. That limit does not rule out every chemical spread, but no large variation was detected. Combined with the lower velocity dispersion, the chemistry looked more consistent with a star cluster than with a dark matter-dominated dwarf galaxy. Yet an ordinary star cluster made of only the visible stars still struggles to explain everything. Even if dark matter is not required, there may be substantial unseen mass in the form of ordinary stellar remnants. White dwarfs, neutron stars, and stellar mass black holes produce very little light compared with normal stars. Over billions of years, mass segregation can concentrate these heavier objects toward the centre, while low-mass luminous stars move outward and escape. Detailed collisional simulations published in 2025 showed that compact remnants might provide between roughly half and 4/5 of the remaining cluster mass in some models of UNIONS 1. These simulations produced longer survival times than earlier dark matter-free models because the first calculations had treated the system as though its observed luminous mass represented nearly all of its matter. When invisible remnants were included, the cluster became heavier, more tightly bound, and capable of lasting for another 2 billion years or more. This creates an amusingly complicated choice between two kinds of darkness. The first is cosmological dark matter, an unknown form of matter that surrounds galaxies and appears to dominate the universe's large-scale mass. The second is ordinary matter that has become difficult to see. Cooled white dwarfs, neutron stars, black holes, and very faint low-mass stars. Both contribute gravity. Only one would make UNIONS one a genuine dark matter-dominated galaxy. Another set of simulations explored the idea of a dark star cluster. Despite the name, this is not a cluster made from the mysterious dark matter of cosmology. It is an evolved star cluster in which much of the remaining mass is contained in dark stellar remnants, especially a central subsystem of black holes. Interactions involving those black holes can transfer energy to luminous stars, push some members outward, and accelerate the loss of visible material. The cluster becomes fainter while retaining an unseen gravitational core. Such simulations can produce apparent mass-to-light ratios reaching into the thousands, or even approaching 10,000, overlapping the region normally associated with dwarf galaxies. They show that an extreme mass-to-light ratio does not automatically prove the presence of cosmological dark matter. A cluster undergoing unusual late-stage evolution can imitate some of the same dynamical signs. There is also the possibility that stars being stripped by the Milky Way are not in equilibrium. Most standard mass estimates assume that a system has settled into a stable arrangement in which the star's random motions balance gravity. If the object is actively dissolving, some measured stars may already be escaping. Their velocities do not describe a quiet bound system, so applying an equilibrium formula can produce an exaggerated mass. This is similar to trying to estimate the strength of a container by measuring the motion of objects after the lid is opened. Some pieces are no longer behaving as part of the original system. Tidal tails, unbound stars, and recent gravitational shocks can all broaden the observed velocity distribution without requiring a large invisible halo. Foreground contamination produces another risk. A star belonging to the Milky Way's general halo may happen to have the right colour, position, and approximate velocity to look like a member. Astronomers combine many clues to reduce this problem, but with a tiny sample, even one interloper can matter. Proper motions from Gaia, detailed metallicities, and repeated radial velocities are all used to refine membership. Rotation could complicate the picture as well. If the stars exhibit an ordered velocity gradient across the object, some of the apparent dispersion might represent rotation rather than random motion. With so few members, detecting a reliable pattern is difficult. The available observations do not establish strong rotation, but the possibility illustrates how many assumptions hide beneath a single number called velocity dispersion. For now, the dark matter halo remains a possibility without positive observational support. That may sound less exciting than the early claim of the darkest galaxy ever discovered, but scientifically it is more interesting than a simple reversal. The object has become a test of how astronomers distinguish galaxies from star clusters at the lowest possible luminosities. It shows where familiar tools begin to struggle, and where several forms of unseen mass can imitate one another. Future measurements could still change the balance. More member stars would reduce the influence of any one binary or outlier. Continued spectroscopy could reveal slow, binary orbits that have not yet been recognized. More precise velocities might finally resolve an intrinsic dispersion close to the stellar expectation or establish a larger value. Deeper imaging could measure the present-day mass function, showing whether low-mass stars have been heavily depleted as cluster simulations predict. Chemical abundances beyond iron may also help. Detailed measurements of elements produced by different kinds of supernovae could reveal whether the stars formed from a single chemically uniform cloud or experienced a more complex enrichment history. That work is difficult because nearly all the members are faint main sequence stars, but future telescopes with larger mirrors may gather enough light. The distribution of stars across the system is another clue. A dark matter-dominated dwarf galaxy should not experience the same degree of ordinary two-body relaxation and mass segregation as a tiny coalitional star cluster. If heavier visible stars are more centrally concentrated than lighter ones, that would support a cluster history, although current surveys may not reach faint enough stars to make the test decisive. Tidal tails would offer additional evidence. A long stream of escaped stars with the same chemistry and motion would show that the Milky Way is actively stripping the system. A dense dark halo could resist disruption and keep the stellar population relatively intact. A cluster near the end of its life might leave a more obvious trail, though the low number of available stars makes even a real stream extremely difficult to find. Gamma-ray searches may continue, but their interpretation must now be cautious. A non-detection cannot strongly constrain dark matter particle models unless the amount and distribution of dark matter in UNIONS 1 are known. The object's early reputation made it appear to be an exceptional laboratory for annihilation searches. The later stellar data remind us that the laboratory itself must first be identified correctly. The story is therefore not that dark matter was discovered in UNIONS 1 and then removed. It is that the first observations allowed a dramatic interpretation, while also containing warnings that more data were needed. New observations answered some questions, exposed binary motion, and shifted the statistical preference toward a stellar system. Dark matter has moved from being the leading explanation to being an unconfirmed possibility. This is how evidence often develops at the faint edge of astronomy. The most distant or least luminous objects provide very little information, and that information arrives one star at a time. A conclusion may depend on a velocity difference smaller than the speed of an ordinary aircraft, measured in light that has travelled for 33,000 years. Every uncertainty has to be examined because there are too few stars for mistakes to average away. UNIONS, one may still be sitting inside a small dark matter halo. It may instead contain a hidden cluster of stellar remnants. It may be out of equilibrium and shedding stars under the Milky Way's pull. Some combination of these possibilities could also be true. A weak halo, a population of remnants, binary motion, and tidal disturbance are not mutually exclusive. Whatever is holding the surviving stars together has been tested repeatedly by the galaxy around them. Their orbit carries them through a changing gravitational field, and every close approach to the Milky Way should stretch the system a little more. If there is no protective dark halo, the question becomes increasingly difficult to avoid. How has such a low-mass object survived for so long? And why has the Milky Way not already pulled its final visible members apart? Without a clearly detected dark matter halo, Ursa Major 3/UNIONS 1 is left facing a difficult problem. It lives close enough to the Milky Way for our galaxy's gravity to dominate its path, yet it contains so little visible mass that its own gravitational hold should be extremely weak. The system is not resting safely in an isolated corner of intergalactic space. It travels through the Milky Way's halo, repeatedly approaching regions where the gravitational field becomes stronger and more uneven. If UNIONS 1 is merely a small collection of ordinary stars, then every one of those passages should loosen it, stretch it, and carry away some of its already limited population. This is what makes its existence so surprising. A satellite of the Milky Way is not the same thing as an object sitting beside the galaxy, in a permanent and comfortable position. A satellite is continually falling around the Milky Way. Its forward motion prevents it from falling directly inward, while the galaxy's gravity keeps bending its path. The same broad principle keeps the Moon around Earth and Earth around the Sun, although the orbit of UNIONS 1 is much larger, slower, and less circular. Based on its measured position, distance, radial velocity, and proper motion, astronomers have reconstructed an orbit that carries the system between a closest approach of roughly 13 kiloparsecs and a farthest distance of around 30 kiloparsecs from the centre of the Milky Way. That corresponds to a range of approximately 42,000 to nearly 100,000 light-years. Its radial orbital period, the time required to move from one close approach outward and back again, is estimated at roughly 400 million years. The precise path depends on the model used for the Milky Way's gravitational field, but the general conclusion is stable. UNIONS. One repeatedly travels through a region where galactic tides should matter greatly. 400 million years is an enormous period from a human perspective. Continents move, species emerge and disappear, and entire branches of life can change during that time. For a stellar system older than 11 billion years, however, it is not especially long. If the current orbital timescale gives even a rough impression of its long-term history, the stars may have completed many journeys around the Milky Way. The exact number cannot be obtained by simply dividing the age by the present orbital period, because the Milky Way has grown and its gravitational field has changed. Even so, UNIONS 1 is unlikely to be experiencing galactic tides for the first time. During every orbit, the danger increases as the satellite approaches pericenter, the point nearest the galactic center. Gravity itself is not the problem. A perfectly uniform pull would accelerate every star in the same way, carrying the entire system along without tearing it apart. The destructive effect comes from the fact that the Milky Way's gravity is stronger on the side of UNIONS, one facing the galactic center, and slightly weaker on the opposite side. This difference is called a tidal force. The same general effect produces tides on Earth, because the Moon pulls more strongly on the side of our planet nearest to it than on the far side. In a stellar system, there are no oceans rising and falling. Instead, the unequal force acts on the orbits of individual stars. Those near the Milky Way facing edge are pulled outward from the satellite in one direction, while stars on the far side experience a relative pull in the other. The result is a gradual stretching of the system along the direction of the surrounding gravitational field. A satellite can resist this stretching if its internal gravity is strong enough. A massive dwarf galaxy has a deep gravitational potential, usually dominated by dark matter. A dense globular cluster can bind its stars tightly through ordinary stellar mass. UNIONS 1, taken only at its observed luminosity and original stellar mass estimate, possesses neither advantage. Its visible stellar mass was estimated at only about 16 times that of the Sun, while half of its light is spread within a radius of roughly 3 parsecs, or close to 10 light-years. That is a remarkably low average density for a system exposed to repeated galactic tides. The region within which a satellite can hold onto material against the gravity of a larger host is often described by its tidal radius, or in orbital calculations, its Jacobi radius. Inside this rough boundary, the satellite's own gravitational influence can dominate the local motions of its stars. Beyond it, the Milky Way has an easier time removing them. The size of this protected region is not fixed. It shrinks when the satellite moves closer to the galactic center, because the host's gravitational field becomes stronger. A star that remains comfortably bound near epicenter may therefore become vulnerable near pericenter. It does not necessarily escape during the first close passage. Tidal disruption is often a slow process. The star may be pushed onto a wider orbit within the satellite, receive another small disturbance during the next passage, and finally cross the boundary after several encounters. Once it escapes, it begins following an orbit around the Milky Way that is similar to, but no longer exactly shared with, the orbit of its former home. Escaped stars tend to leave through 2 broad regions on opposite sides of the satellite. Some move slightly ahead along the orbit, forming a leading tail. Others fall behind, forming a trailing tail. Over time, the tails can grow into a long, thin stellar stream. The original system may eventually disappear, while its stars remain stretched along the path it once followed. The Milky Way's halo contains many such streams. Some came from star clusters, while others are the remains of dwarf galaxies. They demonstrate that our galaxy has been continuously taking apart smaller systems. This process does not require a dramatic collision in which stars crash together. direct stellar collisions are extraordinarily rare in the diffuse halo. The destruction is gravitational. The Milky Way gradually separates the members of a satellite and absorbs them into its own population. For a system as faint as UNIONS 1, the process would be difficult to watch. Even its central concentration was discovered only through careful statistical filtering. Stars spread into tidal tails would be more widely separated and much harder to distinguish from unrelated Milky Way stars. There may be only a few detectable members in the tails, and those stars could extend over a large part of the sky. The absence of an obvious stream therefore does not prove that stripping has not occurred. A stream containing very few luminous stars may simply lie below present detection limits. The first detailed survival calculations made the problem look severe. Researchers modelled UNIONS 1 as a self-gravitating object containing the observed stellar mass but no dark matter. They placed this model on its reconstructed orbit in a representation of the Milky Way's gravitational field and allowed it to evolve. The simulated system lost stars rapidly and was fully disrupted within roughly one future orbital period, about 400 million years. Tests using somewhat different models of the Milky Way and different orbits within the observational uncertainties produced the same general result. A purely stellar system with the observed mass and size was destroyed within a few pericentric passages. This created a timing problem. UNIONS 1 stars are more than 11 billion years old, yet a system resembling its present visible form appeared capable of surviving for only a tiny fraction of that age. Discovering it during the final few hundred million years would mean that we happened to look at exactly the right moment, after it had lost almost everything but shortly before the last recognizable concentration disappeared. Such coincidences are possible. Every dissolving system has passed through a final stage, and any observer living at the right time could discover it then. Astronomy, however, becomes cautious when an explanation requires an extremely narrow viewing window. If a system can exist in its observed condition for only a brief part of cosmic history, researchers naturally ask whether some missing ingredient is allowing it to survive longer. Dark matter was the most direct missing ingredient. A dense dark matter halo could extend far beyond the visible stars and provide enough gravity to resist galactic tides. The Milky Way might strip material from the halo's outskirts, while leaving a dense central remnant intact. The few stars would remain embedded near the centre, protected by mass that could not be seen. In the early dark matter models, UNIONS 1 was placed at the centre of a halo that may originally have contained around 1 billion solar masses. Most of that original halo could have been stripped during its history around the Milky Way, leaving a much smaller but still dense core. Because the central density of a cuspy cold dark matter halo can remain high even after severe outer mass loss, the remnant could continue binding the stars through repeated pericentric passages. Under that interpretation, the stars are not the structure itself. They are merely the visible traces of a much larger gravitational system. Their low number does not make the satellite fragile because the gravity holding them together comes mainly from unseen matter. UNIONS 1 would be similar to a small cluster of lights attached to an enormous structure in darkness. The lights reveal where the centre is, but they tell us very little about the full size or mass of what surrounds them. The later observational evidence weakened the need for this explanation. Repeated spectroscopy expanded the member sample from 11 to 16 stars, revealed at least one important binary, and reduced support for the original high-velocity dispersion. The newer data favour a stellar-only internal dispersion near 1/10 of a kilometre per second over the original estimate of 3.7 kilometres per second, and they provide no current positive evidence for dark matter. The chemical measurements also show no large metallicity spread, making a star cluster identity more likely, although a dwarf galaxy has not been completely excluded. Removing the strong dynamical evidence for dark matter brings the survival puzzle back. If the system is a cluster, why did the early simulations destroy it so quickly? One answer is that those first calculations were deliberately simple. They treated the object as a smooth, collisionless distribution with a total mass close to the estimated visible stellar mass. This was useful for showing how vulnerable such a low-density object would be, but UNIONS 1 contains so few stars that its internal evolution may not behave like a smooth system. In astronomy, the word collisionless does not mean that the members lack gravity or pass through one another physically. It means that individual close gravitational encounters can be averaged away because there are so many particles. A galaxy containing billions of stars is effectively collisionless over much of its life. One star's encounter with another has almost no effect on the galaxy as a whole. A small star cluster is different. Individual stars exchange energy through repeated gravitational encounters. Binary systems interact with passing members. Heavy objects sink toward the center, while lighter ones move outward. Stars evolve and lose mass. Supernova remnants may receive kicks. The fate of one black hole or binary can influence the later structure of a cluster, with only a few thousand original members. Later simulations treated UNIONS 1 as a collisional star cluster, and included stellar evolution, primordial binaries in some runs, mass segregation, and the external tidal field of the Milky Way. Instead of beginning with only the tiny mass visible today, the model started with a more substantial cluster and followed its gradual reduction over about 12 billion years. They produced remnants that resembled the current size and luminosity of UNIONS, 1 while remaining bound without a cosmological dark matter halo. The key was the retention of compact stellar remnants. Massive stars that formed early would have completed their luminous lives long ago. Some became white dwarfs, while others produced neutron stars or black holes. These objects add mass but little or no visible light. In the simulations, compact remnants could account for roughly half to 4/5 of the present cluster mass, depending on the assumed retention of neutron stars and black holes. A cluster containing such remnants is more massive than a count of its visible stars suggests. That greater mass deepens the gravitational potential and makes the system more resistant to the Milky Way's tides. The cluster is still fragile, but not as fragile as an object containing only 16 solar masses. Mass segregation helps concentrate the remnants. Through long-term energy exchange, heavier objects tend to settle toward the center. Lower mass stars are pushed toward wider orbits, where the galactic tidal field can remove them more easily. The visible population therefore becomes increasingly depleted while the darker, heavier core survives. This is a strange but entirely ordinary form of invisibility. No exotic dark matter particle is required. The darkness comes from dead stars. A stellar mass black hole may weigh several or tens of times more than the Sun while producing no detectable light on its own. A neutron star may contain more mass than the Sun inside a sphere about the size of a city. A cooled white dwarf can be extremely faint. Place several of these objects in a cluster 33,000 light-years away, and they can influence the motions of visible stars while remaining hidden from direct observation. The later collisional simulations estimated that a cluster resembling UNIONS 1 might have another 1.9 to 2.7 billion years of life remaining, depending on the fraction of compact remnants retained. That is far longer than the roughly 0.4 billion year survival time from the earlier simplified models. It does not mean the cluster is safe forever. It means that seeing it today no longer requires quite such an unlikely coincidence. Another group of simulations explored an even more extreme possibility, in which stellar mass black holes form a central subsystem. Interactions among the black holes and ordinary stars can inject energy into the visible population, pushing luminous members outward and accelerating their escape. The object becomes progressively fainter while retaining a dark central core made from ordinary stellar remnants. Researchers sometimes call this a dark star cluster. The phrase can be confusing because it does not mean a cluster composed of cosmological dark matter. It describes a star cluster whose mass is increasingly dominated by objects that no longer shine. Such a system may develop an unusually large apparent mass-to-light ratio and can begin to resemble a dwarf galaxy dynamically, even though it formed as a cluster. Simulations suggest that this kind of remnant can occupy the same region of size, luminosity, and apparent mass-to-light ratio as ambiguous ultra-faint satellites. The black holes do not hold the cluster together in a perfectly quiet arrangement. Their interactions can also help destroy it. A binary black hole at the centre may transfer energy to passing stars, causing the cluster to expand and lose members more quickly. Black holes can eject one another during strong encounters. The remaining luminous population dwindles, and eventually the central remnant system also dissolves. In one model matching some of UNIONS 1's properties, the cluster entered a dark cluster phase several billion years ago and was expected to lose its remaining luminous stars within roughly another billion years, followed by the gradual disruption of the black hole subsystem. These values depend strongly on the chosen initial conditions and should not be treated as a firm forecast for the real object. They demonstrate, however, that a nearly invisible stellar system can persist for a significant period while actively approaching dissolution. If that picture is correct, UNIONS 1 may not have survived despite the Milky Way's tides. It may look the way it does because of them. The galaxy's gravity could have removed most of the cluster's original stars, turning a once more ordinary system into the extreme remnant observed today. Its faintness would then be evidence of damage rather than evidence that it was born with only a few dozen members. This distinction changes the meaning of the title, smallest galaxy. Perhaps the object is not a tiny primordial galaxy that formed just enough stars to become visible. Perhaps it is the remaining core of a star cluster that used to be larger. The present scale would tell us about destruction, not formation. Astronomers can test this possibility by measuring the population of low-mass stars. Tidal stripping and mass segregation should preferentially remove lighter members, producing a present-day mass function that differs strongly from the one expected in a dark matter-protected dwarf galaxy. Deep observations could count faint stars across different mass ranges and determine whether the system is missing the low-mass population normally found in an old stellar group. This is a demanding measurement. The stars most useful for the test are among the faintest. From 33,000 light-years away, very low-mass red dwarfs require deep imaging with stable resolution and careful separation from foreground and background objects. The current survey data do not provide a complete enough census to settle the question, but future observations with powerful space telescopes or large ground-based facilities may reach the necessary depths. The spatial arrangement of different stellar masses may provide another clue. In a relaxed star cluster, mass segregation can make heavier visible stars more centrally concentrated than lighter ones. A dark matter-dominated dwarf galaxy has such a long internal stellar relaxation time that ordinary two-body mass segregation should be much weaker. Detecting a clear difference in the radial distributions could support the cluster interpretation. Current simulations warn that the signal may still be subtle. Even when unseen remnants are strongly concentrated, the small number of luminous members can make mass segregation among the visible stars statistically difficult to detect. Once again, UNIONS 1 offers very little evidence and asks astronomers to extract nearly everything from it. A search for tidal tails is equally appealing. A cluster losing stars should leave escaped members distributed along its orbit. Those stars would share similar chemical abundances and related proper motions. If a sequence of matching stars could be traced beyond the compact core, it would provide direct evidence of disruption. The difficulty is that the tails may contain only a handful of detectable stars. Early modelling showed that even a disrupting version of UNIONS 1 would produce very sparsely populated extensions beyond its central region. A survey may identify the compact overdensity while failing to distinguish the escaped members from the far larger Milky Way foreground. The system's shape might also reveal stress. Strong tides can stretch a satellite along its orbit, giving it an elongated appearance. Yet the measured shape of such a sparse object is uncertain. Moving one probable member into or out of the sample can alter the inferred ellipticity. An apparently round core does not rule out stripping, and an apparently elongated one may be influenced by small number statistics. Repeated velocity measurements remain essential. A star already escaping from the system could broaden the measured dispersion, imitating extra mass. Binary orbital motion can do the same. Foreground interlopers add another source of confusion. Astronomers must determine not only how fast the stars move, but whether each measured motion represents the stable gravitational system they are trying to weigh. UNIONS 1 therefore lives in an awkward observational state. It is definitely a real co-moving satellite, but almost every detail of its internal structure is difficult to measure. It may be bound tightly enough to survive for billions of years, or it may be approaching final dissolution. It may contain a weak dark matter halo, a concentrated population of stellar remnants, or both. It may have lost most of its original stars, yet the number and distribution of those lost members are unknown. Calling it the Milky Way's faintest known satellite is currently safer than insisting that it is the Milky Way's faintest galaxy. The word satellite describes its gravitational relationship with our galaxy, without settling what sort of object it is. It travels around the Milky Way, belongs to the broader halo population, and has survived long enough to be discovered. Whether it crossed that long history as a protected dwarf galaxy, or as a cluster slowly stripped toward extinction, remains uncertain. From somewhere near one of its visible stars, the Milky Way would dominate the surroundings in a way that is difficult to imagine from Earth. Our galaxy would not necessarily appear as the same thin band seen from the solar system, because UNIONS 1 lies outside the main disk and views it from a different angle. Much of the disk could appear as a broad, luminous structure, with the central regions brighter and denser than the outskirts. The satellite's own stars would provide only a sparse local sky. There would be no clear visual sign of the dark matter that might surround it, and no obvious boundary marking where the satellite ended and the Milky Way began. A star gradually pulled away would not pass through a wall. Its orbit would simply become less controlled by the small system and more completely controlled by the galaxy. That transition happens slowly. A star can spend long periods near the edge, receiving repeated gravitational nudges. Eventually it drifts away from the core and joins the halo. After enough stars follow, the original system becomes harder to identify. Nothing explodes. No final light switches off. The relationship that defined the group simply weakens until the stars no longer move as one object. UNIONS 1 may currently be somewhere along that process. Its small population, unusual mass-to-light possibilities, ancient age and close orbit all suggest that it has endured substantial evolution. The Milky Way has either failed to destroy it because unseen mass continues to protect it, or it has already destroyed nearly all of it and left only the compact remnant that astronomers found. Both possibilities lead to the same uncomfortable question. When only a few stars remain, what feature decides whether the surviving system deserves to be called a galaxy? For most familiar objects in the universe, deciding what to call them is not especially difficult. A star is not easily confused with a planet once its light, mass, and energy source are understood. A large spiral galaxy does not resemble an ordinary star cluster. The Milky Way contains hundreds of billions of stars, large quantities of gas and dust, a central black hole, and a vast halo of dark matter. A typical star cluster is much smaller, contains far fewer stars, and is held together primarily by the gravity of its ordinary matter. Place the two side by side and no one needs to spend several years measuring the motions of 16 faint stars before choosing a label. Ursa Major, 3/UNIONS, 1 does not offer that convenience. It lies exactly where the familiar categories begin to overlap. Its physical size resembles that of a compact star cluster. Its ancient and extremely metal-poor stellar population could belong to either a cluster or an ultra-faint dwarf galaxy. Its total luminosity is lower than that of any confirmed galaxy, but faintness does not automatically disqualify it. The first velocity measurements suggested an enormous quantity of dark matter, while later observations found that the same motions could be consistent with a system made from stars and stellar remnants alone. Every promising clue seems to arrive carrying a small note that says, "Please check again." The basic difference between a galaxy and a star cluster is often described through dark matter. In the standard picture of cosmic structure, galaxies form inside halos of dark matter. Gas falls into these halos, cools, and produces stars. Star clusters form from dense clouds of ordinary gas, usually within galaxies, and do not require their own extended dark matter halos. A useful scientific definition proposed by astronomers Beth Willman and Jay Strader describes a galaxy as a gravitationally bound collection of stars whose observed properties cannot be explained by ordinary matter acting under Newtonian gravity. Under the standard cosmological interpretation, the missing ingredient is usually dark matter. A star cluster, by contrast, can be explained as a self-gravitating collection of stars, binaries, gas during its youth, and the remnants left after stars die. That definition is more practical than saying a galaxy must contain a particular number of stars. Nature provides no official minimum attendance. There is no known rule stating that 59 stars make a cluster while 60 make a galaxy, though cataloguing would certainly be quicker if there were. A system could contain very few visible stars and still be a galaxy if those stars occupied a dark matter halo. Another system could contain millions of stars and still be a cluster if ordinary matter fully explained its structure and motion. Size cannot settle the question either. Galaxies generally extend over larger regions than star clusters of similar luminosity, but the categories overlap. Some diffuse star clusters are broad, while some faint satellites are compact. UNIONS 1 has a half-light radius of approximately 3 parsecs, or around 10 light-years. That places it comfortably among cluster-like dimensions. Many confirmed ultra-faint dwarf galaxies have half-light radii measuring tens or hundreds of parsecs. Yet physical compactness alone does not prove that UNIONS 1 lacks dark matter. A galaxy can lose outer material through tidal stripping, leaving a compact stellar remnant near the centre of a surviving halo. Brightness is equally unhelpful as a strict boundary. UNIONS 1 produces only about 11 times the visual luminosity of the Sun, making it the faintest known Milky Way satellite. If confirmed as a galaxy, it would be the least luminous galaxy ever identified. If classified as a star cluster, it would rank among the faintest and most metal-poor clusters known. The same measurement creates a record in either category without telling us which category is correct. The first major test involves dynamics, meaning how the stars move under gravity. Astronomers measure the radial velocities of individual members and calculate the velocity dispersion, the amount by which those speeds vary around the system's average motion. A low-mass star cluster should have a very small internal dispersion. A galaxy embedded in a dark matter halo can keep stars bound, even when they move more rapidly. Initial Keck observations of 11 likely unions, one member suggested a dispersion of about 3.7 kilometers per second. That was far too large to be explained by the estimated visible stellar mass. Taken literally, it implied an extreme dynamical mass-to-light ratio and made the system appear to be one of the most dark matter-dominated objects ever found. This was the strongest early reason for describing it as a galaxy. There was, however, an immediate difficulty. The result depended heavily on 1 or 2 stars. Removing the largest velocity outlier reduced the inferred dispersion substantially, and removing another left it unresolved. With only 11 measurements, one unusual member could change the classification of the entire system. A star in a binary could appear unusually fast because it was orbiting an unseen companion. A Milky Way foreground star could be mistakenly accepted as a member. A star being pulled away by galactic tides might not reflect the motion of a stable, bound system. Later spectroscopy was designed to examine exactly those possibilities. Researchers obtained improved measurements for 16 members, including repeated observations capable of revealing changing velocities. At least one influential star was identified as a binary, and additional stars showed possible binary behaviour. The newer data placed an upper limit of 2.3 km per second on the intrinsic dispersion and strongly favoured the approximately 0.1 km per second value expected from a stellar system over the original 3.7 km per second result. The authors found no current observational requirement for dark matter. That does not prove that the system contains no dark matter. An unresolved dispersion means the motions are too small, the sample too limited, or the uncertainties too large to measure the true value confidently. A modest dark matter halo could still hide within the allowed range. What disappeared was not dark matter itself, but the strong evidence that required it. The second major test comes from stellar chemistry. A galaxy's dark matter halo can provide a gravitational well deep enough to retain some gas after the first massive stars explode. Supernovae enrich that gas with iron and other heavy elements. If the system later forms another generation of stars, those younger members are born from more enriched material. The result is a spread in metallicity, with different stars preserving different stages of chemical evolution. A small star cluster usually forms most of its stars from one cloud over a relatively short period. When massive stars explode, the cluster's shallow gravity cannot retain much of the high-speed ejecta. The remaining stars therefore tend to share a comparatively narrow iron abundance. A measurable internal metallicity spread can provide indirect evidence that an object once possessed a deeper gravitational potential than its stars alone could create. Unions. One is extremely metal poor. Measurements of 12 members found a mean iron abundance around -2.65 on the logarithmic scale used by astronomers. That places it among the most chemically primitive stellar systems in the Milky Way. More importantly for its classification, the observations did not reveal a large internal metallicity spread. The study placed a 95% upper limit of about 0.35 dex on the dispersion. The available chemistry is therefore more consistent with a star cluster, although the limit is not precise enough to exclude every smaller spread that a very faint galaxy might contain. The absence of a detected spread is not as decisive as the presence of one. A clear variation in iron would be strong evidence for repeated enrichment, and therefore for a galaxy-like gravitational history. No detected variation may simply mean that too few stars have been measured, or that the true differences are smaller than the uncertainties. Unions. One offers only one known red giant, forcing astronomers to obtain metallicities from much fainter main sequence stars. Even with large telescopes, those measurements are difficult. A genuine ultra-faint dwarf galaxy could also have formed almost all of its stars during one brief early episode. If star formation ended before several rounds of enrichment occurred, its metallicity spread might be modest. The smallest galaxies formed inefficiently, and some may have produced only a few supernovae before losing their gas. Chemical uniformity leans toward the cluster interpretation, but it cannot act as a universal veto against a galaxy. Age provides even less separation. Both globular clusters and ultra-faint dwarf galaxies can contain populations older than 11 billion years. Many of the Milky Way's globular clusters formed early. Ultra-faint galaxies are also dominated by ancient stars and are often regarded as fossils of the first period of galaxy formation. Unions, one's age tells us that it is a survivor from the early universe, but not whether it was born inside its own dark halo. Its very low metallicity is unusual for a cluster, although not impossible. Star clusters display a broad range of chemical compositions, and several extremely metal-poor examples are known. Galaxies follow a general relationship in which lower luminosity systems tend to have lower average metallicities. Unions 1 lies in an extreme region where either interpretation can be made plausible. It could be a remarkably metal-poor cluster, or a galaxy whose tiny stellar population formed from very primitive gas. Another proposed separator is internal relaxation. In a star cluster, Repeated gravitational encounters between individual stars gradually redistribute energy. More massive stars and remnants tend to settle toward the centre, while lower mass stars migrate outward. This process is called mass segregation. A dwarf galaxy dominated by a smooth dark matter halo is often treated as effectively collisionless, meaning encounters between individual stars should not reorganize the entire population significantly during the age of the universe. At first glance, this seems like an excellent test. Find strong mass segregation, and the object is probably a star cluster. Find none, and it may be a galaxy. Unfortunately, the universe has again declined to make the distinction quite that simple. Recent simulations show that some mass segregation can develop even when stars are embedded in a dark matter halo, particularly in compact ancient systems with short crossing times. The effect may be weaker or proceed differently, but its presence alone does not guarantee a dark matter-free cluster. Strong galactic tides can also remove low-mass stars after they migrate outward, altering the visible pattern. Researchers have specifically modelled UNIONS 1 and warned that mass segregation must be applied cautiously as a classifier. The small number of visible members causes another problem. Even if the heavier stars are slightly more concentrated than the lighter ones, there may not be enough of either group to measure the difference confidently. Simulations of UNIONS 1 as a star cluster found substantial dynamical evolution and strong depletion of low-mass stars, yet the remaining visible population did not necessarily show statistically obvious mass segregation. The most useful evidence may therefore come not from where different stars are located, but from how many low-mass stars remain. This leads to the present-day mass function. When a stellar population forms, it contains many low-mass stars and fewer high-mass ones. The high-mass stars evolve rapidly and become remnants. In an old cluster exposed to tides, low-mass stars are gradually pushed outward and stripped by the Milky Way. After billions of years, the surviving population should be unusually deficient in low-mass members. A dark matter-dominated dwarf galaxy should protect its stars more effectively. It may retain a mass function closer to the original distribution, although tidal stripping can still alter it if the dark halo has been severely damaged. Deep imaging capable of counting very faint stars could therefore test whether UNIONS 1 looks like an evolved, heavily stripped cluster. The 2025 collisional models identified this measurement as one of the most promising ways to determine the system's nature. Counting those stars will not be easy. Low-mass members are extremely faint at a distance of roughly 33,000 light-years. Foreground stars and unresolved background galaxies contaminate the images. Binary systems can appear brighter than equivalent single stars. Astronomers will need precise, deep observations over enough area to include both the centre and outskirts. Compact stellar remnants create another ambiguity. A high mass-to-light ratio is usually interpreted as evidence for dark matter, but a cluster can become dark for more ordinary reasons. White dwarfs, neutron stars, and stellar mass black holes retain mass after their visible lives end. Mass segregation can concentrate them in the centre, while low-mass luminous stars escape. Collisional simulations have shown that UNIONS 1 could survive as a dark matter-free star cluster for another roughly 2 to 3 billion years if it retains enough compact remnants. In some models, those remnants provide most of the remaining mass. The cluster would then possess far more gravity than its visible stars suggest, but the unseen component would consist of ordinary stellar remains rather than cosmological dark matter. Other models explored a central subsystem of stellar mass black holes. Interactions involving these black holes can increase the motions of luminous stars and create an apparently high dynamical mass-to-light ratio. Such a dark star cluster can occupy the same observable region as an ultra-faint dwarf galaxy. It may look too dynamically active for its visible mass, even though no extended dark matter halo is present. This is why the word invisible must always be handled carefully. Invisible mass is not automatically dark matter. It can be an unseen companion in a binary, a population of cooled white dwarfs, neutron stars, black holes, or ordinary low-mass stars below the detection limit. It can even be an illusion created by applying an equilibrium mass estimate to stars that are already escaping. The shape and tidal condition of the system provide additional clues, though neither is decisive. A star cluster close to dissolution may be elongated along its orbit and surrounded by leading and trailing tails. A dwarf galaxy inside a dense halo should be more resistant to stripping. Detecting a clear stream of chemically and dynamically related stars would support a cluster being torn apart, or at least show that the object has experienced severe tidal damage. A dwarf galaxy can also produce tidal tails after losing enough of its dark halo. The remains of destroyed galaxies form some of the Milky Way's largest stellar streams. Tidal features therefore reveal disruption, but do not necessarily identify the original object. In UNIONS 1's case, the tiny number of available stars makes any stream extraordinarily hard to find. A few escaped members spread across the halo may be almost indistinguishable from the general stellar background. Orbital survival once seemed to favour a galaxy strongly. Early models found that a self-gravitating system containing only the observed stellar mass would dissolve in around one orbital period, roughly 400 million years. A dark halo appeared necessary to explain why an 11 billion-year-old object remained visible today. The newer collisional models weakened that argument. By beginning with a larger star cluster and including stellar evolution, binaries, mass segregation, compact remnant retention, and long-term loss of low-mass stars, researchers produced remnants that resembled present-day UNIONS 1. These models survive much longer than the original simplified systems. The Milky Way's gravity may have reduced the cluster to its current state without completely destroying it yet. A cluster origin also provides a natural explanation for the system's compact size and apparently uniform chemistry. It could have begun with several thousand stars, lost nearly all of them over billions of years, and now be approaching the last stage of dissolution. The few visible members would not represent the small population with which it was born. They would be the survivors of a much larger cluster. A galaxy origin tells a very different story. UNIONS. One may have formed inside a small early dark matter halo, produced only a tiny amount of starlight, and then lost most of its halo, and perhaps many stars to the Milky Way. The present object would be the dense centre of a once larger dark structure. Its compactness would result from severe stripping, while its limited chemical range could reflect a short period of early star formation. Both stories can be adjusted to fit much of the current evidence. That does not make them equally likely. The improved velocity measurements and lack of a large detected metallicity spread now make the star cluster explanation more consistent with the data. Recent researchers have stated that UNIONS 1 is likely a star cluster, perhaps one stabilized by a substantial unseen population of stellar remnants, while emphasizing that the dwarf galaxy interpretation has not been completely ruled out. As of 2026, the most careful label is therefore Extreme Milky Way Satellite, or Likely Star Cluster, and Former Galaxy Candidate. Calling it definitively the smallest galaxy would go beyond the available evidence. Calling it an ordinary cluster would also understate how unusual it is. It occupies a nearly empty part of the known size and luminosity landscape, and may represent a kind of evolved remnant that surveys have rarely been able to detect. The uncertainty also exposes a limitation in the way astronomical categories are often imagined. Galaxies and star clusters are not defined by appearance alone. They are defined partly by formation history and invisible structure. Two objects can have the same radius, brightness, age, and approximate number of stars while having very different origins. One may have formed at the centre of a dark matter halo. The other may have formed as a dense cluster inside a larger galaxy. Billions of years of stripping can make their present-day properties overlap. The boundary can become even less tidy if a star cluster forms inside a dwarf galaxy and later survives after its host is destroyed. It may contain stars with a complex chemical history inherited from the galactic environment, but possess little or no dark matter today. A stripped galactic nucleus may look like a massive cluster. A cluster embedded in a small early halo might retain some dark matter. Formation and later evolution do not always preserve the clean categories used in introductory diagrams. Unions, one may eventually receive a firmer classification through several measurements working together. A resolved internal velocity dispersion significantly above the stellar prediction would revive the dark matter case. A definite spread in iron abundance would indicate chemical self-enrichment and favour a galaxy. A sharply depleted low-mass stellar population would support heavy cluster evolution. Clear mass segregation, a central concentration of remnants, or a tidal stream could strengthen that picture further. Future observations may also measure detailed chemical abundances beyond iron. Elements created by core collapse supernovae, neutron capture processes, and other stellar events can reveal whether all the members formed from one well-mixed cloud or from gas altered over time. A dwarf galaxy with only a handful of ancient stars might preserve a complicated chemical signature, even when its overall iron spread is small. Longer monitoring will improve the binary census. Some companions take years or decades to reveal their orbits. Until binary motion is understood, the internal velocity dispersion cannot be measured with complete confidence. Each confirmed stable member reduces the uncertainty, but there may never be hundreds of suitable stars available. Unions, one is so faint that the usual solution of collecting a much larger sample may not be possible. The object therefore teaches an important lesson about minimum galaxies. The lower boundary is not set simply by the number of stars we can count. It is set by the smallest dark matter halo capable of forming and preserving a detectable stellar population, combined with the smallest amount of evidence we need to demonstrate that the halo exists. Those are two different limits. Nature determines the first. Our telescopes and methods determine the second. Unions, one may lie below the natural galaxy threshold and be a dissolving cluster. It may sit just above that threshold while remaining too difficult for present observations to prove. Until the distinction is resolved, its title has to carry an asterisk. It is the smallest known galaxy only under the condition that it is a galaxy at all. That condition does not diminish the object. It is the reason the system matters. A clear, ordinary dwarf galaxy would add one more member to the Milky Way's satellite population. An ambiguous object forces astronomers to test what each classification means, how dark matter is inferred, how clusters dissolve, and how little light can remain connected to an ancient gravitational history. Somewhere in the direction of Ursa Major, 16 spectroscopically confirmed stars continue moving together, while researchers debate the origin of their shared motion. Those stars do not change because the label changes. They remain old, metal-poor, compactly distributed, and exceedingly faint. The disagreement belongs to us, because we are trying to reconstruct billions of years of history from the limited information that reaches our telescopes today. For the moment, the evidence leans toward a star cluster, but the possibility of a true galaxy remains open enough to keep the object's original claim alive. The question sounds simple enough. Is Unions one really the smallest galaxy in the universe? We have measured its light, estimated its size, identified stars that move with it, and followed its orbit around the Milky Way. It appears to contain only a few dozen visible stars. Half of its light comes from within a radius of about 3 parsecs, and all of that light combined is equivalent to only around 11 suns. Surely after collecting those numbers, astronomers should be able to place the object at the bottom of a list and give it a small but well-earned trophy. The difficulty is that the word smallest does not have one agreed astronomical meaning. An object can be small in physical size, small in stellar mass, small in total luminosity, small in the number of stars it contains, or small in the mass of the dark matter halo that formed it. Those measurements are related, but they are not interchangeable. A galaxy can be physically broad while producing very little light. Another can be compact but contain a dense population of stars. A third may contain hardly any visible matter while occupying a much larger invisible dark matter halo. UNIONS 1 is extreme in several categories at once. Its absolute visual magnitude is about plus 2.2, making it fainter than every confirmed Milky Way dwarf galaxy. Its half-light radius is approximately 3 parsecs, much smaller than those of most recognised dwarf galaxies. The original estimate placed its stellar mass at only about 16 times the mass of the Sun. If it is genuinely embedded in its own dark matter halo, then it would be the least luminous, and perhaps the least populated galaxy known. The trouble, as we've seen, is that the latest multi-epoch spectroscopy does not presently require that dark matter halo. The same system may instead be an extraordinarily faint star cluster. The fairest answer in 2026 is therefore slightly inconvenient. UNIONS 1 is the faintest known satellite of the Milky Way, and it is a candidate for the smallest known galaxy, but it is not yet secure enough to be called the smallest confirmed galaxy. The improved velocity measurements and the lack of a large detected metallicity spread currently lean toward a star cluster interpretation. A separate Bayesian analysis of the earlier velocity sample found little evidence that rotation supports the system and continue to regard both a dwarf galaxy and a self-gravitating cluster as viable, but that work also emphasized how strongly the inferred mass changes when only 1 or 2 stars are removed. The classification remains open, with the newer repeated observations providing the strongest direct warning against treating the original dark matter estimate as settled. That does not make the title meaningless, it makes it conditional. If future observations reveal a genuine velocity dispersion above what ordinary stars and stellar remnants can produce, or if they uncover a clear chemical spread showing that the system formed several stellar generations, then UNIONS 1 could return to the galaxy category with a much stronger case. At that point, its extraordinarily low luminosity would push the known galactic boundary far below anything confidently established before. For comparison, Segway 1 remains one of the faintest and smallest securely classified dwarf galaxies. It has an absolute visual magnitude of about minus 1.5, a stellar mass of roughly 500 suns, and a half-light radius near 29 parsecs. Repeated velocity measurements show that its stars move too quickly to be held by their visible mass alone, even after binary stars are considered. Its members also display a real spread in metallicity, demonstrating that the system experienced chemical enrichment, rather than forming as one simple stellar population. Segway 1 is faint enough that its total luminosity is lower than that of a single bright red giant, yet it is still far more luminous, more massive in stars, and physically larger than UNIONS 1. Place the two systems beside each other in an imaginary catalogue, and the difference becomes remarkable. Segway 1 contains only a few hundred solar masses in stars, which is already almost absurdly little for a galaxy. UNIONS 1 may contain only a few tens. Segway 1 spreads its stars across dozens of parsecs. UNIONS 1 concentrates half its light within 3. Segway 1 has enough measured members and chemical evidence to satisfy the usual galactic tests. UNIONS 1 offers only 16 spectroscopically confirmed stars and asks astronomers to make the same decision with much less information. If UNIONS 1 turns out to be a cluster, Segway 1 and other confirmed ultrafaint dwarfs continue to define the lower observed edge of the galaxy population. That does not mean they define the true natural limit. They define only the faintest objects we have found and successfully classified. Somewhere in the Milky Way's halo there may be galaxies with fewer stars than Segway 1 but more stars than UNIONS 1. There may be systems equally faint but farther away, hidden because their individual stars fall below survey limits. Others may lie behind crowded regions of the galactic disk, where dust and foreground stars make statistical searches much harder. The phrase, smallest galaxy in the universe, also reaches beyond the Milky Way. Our own galactic neighbourhood is the only place where astronomers can resolve individual stars in objects this faint, a galaxy containing a few hundred stars would be effectively impossible to recognize at the distance of another large galaxy, unless its members included an unusually bright star or a short-lived event. From millions of light-years away, it would not create a visible smudge. Its stars would be too faint and too sparsely distributed to stand apart from the background. This creates a strong observational bias. The smallest galaxies we know are almost all nearby satellites, because proximity allows us to identify their individual stars. That does not mean the Milky Way owns the universe's smallest galaxies. It means our telescopes can perform the required stellar detective work only within a limited volume. Other large galaxies may possess equally tiny companions that remain undetected, and isolated examples may drift beyond any environment where present surveys could recognize them. Even within the Milky Way, the census is incomplete. A recent uniform search across data from the Dark Energy Survey, DELVE and PAN-STARRS recovered 49 of 62 known satellites inside its usable footprint, illustrating how detectability depends on brightness, size, distance, sky position, stellar crowding, and survey coverage. Modern cold dark matter models also predict that a significant fraction of the Milky Way's faint satellite population has not yet been found. Calling any current object the smallest in the entire universe is therefore a little like identifying the smallest pebble on a beach after examining one carefully chosen square meter. The pebble may genuinely be the smallest in your sample. It may even be impressively tiny. There is simply no reason to assume the rest of the beach has agreed not to produce anything smaller. Astronomers usually prefer the phrase smallest known for exactly this reason. Known is doing important work. It separates an observational record from a universal law. UNIONS 1 is the faintest known Milky Way satellite. If confirmed as a galaxy, it would be the least luminous known galaxy. Neither statement claims that nature cannot make anything fainter. The deeper question is how small nature actually can make a galaxy. At some point, a dark matter halo becomes too light to gather gas, cool it, and form stars. Below that point, the halo may still exist, but it remains dark. It participates in the gravitational structure of the universe without ever producing a visible stellar population. The minimum galaxy is therefore not necessarily the minimum halo. It is the minimum halo that managed to turn at least some ordinary matter into stars. This threshold was not the same throughout cosmic history. Before the universe was reionized, small dark matter halos could cool gas through molecular hydrogen. Molecular hydrogen is not a particularly efficient coolant, but it allowed gas in some early mini-halos to lose energy, collapse, and form stars. Larger halos could cool through atomic hydrogen and were more reliable sites of star formation. Which halos succeeded depended not only on mass, but on when they formed, how rapidly they grew, the local radiation field, the motion between dark matter and ordinary matter, and whether earlier stars had enriched nearby gas with heavier elements. Recent modelling shows that molecular hydrogen cooling may allow some halos below the traditional atomic cooling threshold to form stars before reionization. It also predicts that the process is highly selective. Many halos of similar final mass remain dark because their growth histories never carry them above the necessary cooling conditions at the right time. There may therefore be no single clean mass at which every halo suddenly becomes a galaxy. Instead, there is a transition region in which some halos form stars and others do not. Imagine two early dark matter halos with nearly equal mass. One assembles slightly earlier, when the surrounding gas is cooler and the ultraviolet background is weaker. It gathers enough molecular hydrogen for a small cloud to collapse. A few massive stars form, and perhaps a population of low-mass stars follows. The other halo grows more slowly. By the time it reaches a similar mass, radiation from the first stars and galaxies has heated or dissociated the gas. It never forms a single star. Billions of years later, the first halo may be called an ultra-faint dwarf galaxy, while the second remains an invisible subhalo. Their difference began with timing rather than a dramatic difference in present mass. Reionization made this division sharper. During the universe's first billion years, ultraviolet radiation from early luminous sources ionized the hydrogen between galaxies and heated the intergalactic gas. Small halos with shallow gravitational wells struggled to capture or retain that hotter material. Some tiny galaxies that had already formed stars were quenched. Halos that had not yet begun may have lost their chance almost entirely. The smallest surviving galaxies may therefore be fossils from a narrow period. They formed enough stars before or during reionization to remain visible, but not enough to continue building a large stellar population afterward. Their ancient stars are the evidence that they crossed the threshold just before the universe made the task much harder. If UNIONS 1 is a galaxy, it may represent an extreme version of this history. A tiny early halo might have gathered a small quantity of gas, formed only dozens or hundreds of stars, and then stopped. The most massive members would have died long ago. Some low-mass stars would remain today, providing the few points of light detected in the survey. The surrounding halo could have lost most of its outer dark matter during repeated orbits around the Milky Way, while preserving a dense central core. That scenario would demonstrate that the process of becoming a galaxy can be remarkably inefficient. A dark matter structure many millions of times more massive than the visible stars might produce only enough lasting light to equal a small group of suns. Almost the entire object would be invisible. The term galaxy would refer less to what we see than to the gravitational and formative history inferred around it. Yet there may be a practical lower limit to how few stars can establish that history. Suppose a dark matter halo formed only one star. Would that be a galaxy? Physically, the halo may have crossed the threshold for star formation. Observationally, one star would not reveal the halo. It would look like an ordinary member of the Milky Way. Even if the star moved within an invisible potential, there would be no second tracer with which to compare its motion. A system with 2 or 3 stars would present the same problem. Astronomers could not reliably measure a velocity dispersion, identify a shared chemical history, or distinguish the group from a chance alignment. Nature might create such objects, but science would struggle to recognize them. The minimum observable galaxy therefore requires enough luminous traces to demonstrate that something more than a loose handful of stars is present. This creates 2 lower boundaries. The physical boundary asks how little dark matter and gas are needed to form any stars. The observational boundary asks how many surviving stars are needed for us to prove that the system formed as a galaxy. UNIONS 1 may sit between them. It could be physically galactic while remaining observationally ambiguous. There is no guarantee that every galaxy stays above the observational boundary. Tidal stripping can remove stars and dark matter after formation. A small galaxy may begin with thousands of stars and lose nearly all of them to a larger host. Its final remnant might contain only a few visible members, even though its origin was undeniably galactic. At some point, the evidence of that origin becomes too faint to recover. The reverse confusion also occurs. A star cluster may begin with thousands of stars, lose most of its luminous members, and become dominated by black holes, neutron stars, and white dwarfs. Its visible population may move as though large amounts of unseen mass are present. It begins to imitate the properties used to recognize a tiny galaxy. That is one reason UNIONS 1 is so useful. It is not merely testing the smallest possible galaxy. It is testing whether our diagnostic methods continue to work when the available population becomes extremely sparse. The label may ultimately depend on evidence that has not yet been collected. A precise present-day mass function could show whether low-mass stars has been depleted, as expected in a heavily evolved cluster. More detailed chemical measurements could uncover a small metallicity spread that current data cannot resolve. Continued velocity monitoring could identify additional binaries and determine whether any intrinsic dispersion remains after their orbital motion is removed. A tidal stream could reveal extensive stripping, while a clean, compact system with a measurable dark component would strengthen the dwarf galaxy case. Until those measurements arrive, the responsible conclusion is not especially dramatic, but it is scientifically useful. UNIONS. One may be the smallest galaxy we have ever encountered, but the current evidence makes it more likely to be an extreme star cluster. Its claim remains possible rather than confirmed. The natural lower limit of galaxies is almost certainly not represented by one perfectly defined object. Galaxy formation appears to become probabilistic at very low halo masses. Some halos form a few stars, others remain dark, and still others may form stars only to lose them later. The transition from galaxy to non-galaxy may therefore resemble a fading population rather than a hard wall. A large galaxy such as the Milky Way is easy to identify because every major sign agrees. It contains a complex stellar population: gas, dust, dark matter, active star formation, and a long chemical history. Near the minimum scale, those signs vanish one by one. Gas disappears, star formation stops, chemical enrichment becomes limited, the visible population shrinks, internal motion becomes difficult to measure. Eventually only a few old stars remain, and classification depends on traces of an invisible past. That brings us away from the title of the smallest galaxy and toward what these faint systems reveal about everything we cannot see. UNIONS. One matters whether it wins the record or not. Its uncertainty tells astronomers that the hidden universe is not divided neatly into bright galaxies, dark halos, and ordinary clusters. At the lowest masses, those populations overlap observationally, and understanding the difference can test the foundations of galaxy formation. The Milky Way is surrounded by an enormous halo of dark matter. Within that halo, cosmological models predict many smaller concentrations called subhalos. Some are expected to host satellite galaxies, others should contain no stars at all. The exact number and internal structure of these subhalos depend partly on the physical nature of dark matter. In the standard cold dark matter picture, dark matter particles move relatively slowly during the early growth of structure. This allows matter to collect on very small scales, producing many low-mass halos. Larger halos form through mergers and continued accretion, while a population of smaller subhalos survives inside them. A galaxy like the Milky Way should therefore be surrounded by far more dark structures than the number of bright satellites visible in photographs. This difference once became known as the missing satellites problem. Early dark matter-only simulations predicted many more subhalos than the number of dwarf galaxies known around the Milky Way. The apparent mismatch was not necessarily a failure of the dark matter model. Simulations were counting dark structures, while observations were counting structures with stars. Once reionization, gas cooling, stellar feedback, tidal destruction, survey incompleteness, and the uncertain relationship between halos and galaxies are included, many subhalos are expected to remain dark and many luminous satellites are expected to remain undiscovered. Modern studies can reproduce the known satellite population more successfully, but the faint end remains uncertain. A 2026 model combining a very high-resolution Milky Way halo simulation with galaxy formation physics predicted that the total number of satellites down to extremely low luminosity should not exceed a few hundred, while still leaving a large population of ultra-faint systems missing from the current census. The study also suggested that some compact ambiguous satellites could be dark matter-dominated dwarfs whose stars survive inside dense central cusps. That is a prediction, not a confirmed description of UNIONS 1, but it shows why classifying objects like it matters. If many ambiguous compact systems turn out to be galaxies, the Milky Way could be surrounded by a population of tiny luminous traces marking dense dark matter subhalos. If most turn out to be dissolving star clusters, the number of confirmed low-mass galaxies would be smaller, and the threshold for star formation might lie at higher halo masses. Each classification changes the inferred connection between visible satellites and invisible structure. This connection can test alternatives to cold dark matter. Warm dark matter, for example, would move more rapidly in the early universe and suppress the formation of the smallest halos. Other models allow dark matter particles to interact with one another, altering the density profiles and survival of subhalos. Ultralight particle models can smooth structure below characteristic scales. Primordial black holes or other compact objects could heat the stars of ultrafaint systems through gravitational encounters. The faintest galaxies are useful because they occupy the scales where these differences become strongest. A large galaxy contains so much ordinary matter that gas cooling, star formation, supernova, and black holes can reshape its centre. An ultra-faint dwarf has formed very few stars, so its dark matter halo may remain closer to its original state. The system becomes a relatively clean test, provided astronomers first established that it really is a galaxy. UNIONS 1 briefly appeared to offer an unusually strong opportunity. Its original velocity dispersion implied a very high dark matter density packed into a tiny region. If that interpretation had survived, the object could have placed powerful limits on dark matter particles and annihilation models. Gamma-ray researchers examined its direction because a dense nearby halo could produce a strong signal if dark matter particles annihilate. No significant emission was found, but the usefulness of that non-detection depended on the uncertain dark matter content. The later kinematic evidence weakened those claims. Without a secure halo mass, astronomers cannot confidently turn a missing gamma-ray signal into a strict statement about dark matter particles. This is an important lesson. An extreme object may appear to offer an exceptional physics laboratory, but the laboratory has to be understood before its result can be trusted. A star cluster classification would not make UNIONS 1 irrelevant to dark matter. It would still improve the census by removing one object from the galactic sample and placing it in the cluster population. Knowing what is not a galaxy helps astronomers determine how many dark matter halos successfully formed stars. It also exposes the ways that binary stars and stellar remnants can imitate dark matter, improving the analysis of other faint systems. The system may even teach us about black holes left behind by ordinary stars. Simulations show that a nearly dissolved cluster can retain a central population of compact remnants, including stellar mass black holes. These remnants can add unseen mass, alter the motions of visible stars, and prolong or reshape the cluster's final stages. A tiny satellite that first attracted attention as a dark matter candidate could instead reveal how ordinary stellar death creates a dark cluster. That possibility is less exotic than cosmological dark matter, but it is hardly uninteresting. Black holes may interact in the centre, form binaries, eject stars, and occasionally merge. Such systems could contribute to the population of gravitational wave sources. They also provide laboratories for studying the late evolution of star clusters under strong galactic tides. The distinction between a black hole-rich cluster and a dark matter-rich dwarf becomes difficult because both can have high mass-to-light ratios. The invisible mass has a different distribution, however. Stellar remnants should be concentrated near the centre through mass segregation. A dark matter halo should extend farther beyond the visible stars. Precise stellar motions at different radii could eventually distinguish these profiles, though UNIONS 1 contains so few traces that the task is exceptionally demanding. The chemistry of the faintest galaxies offers another path into the hidden past. A very small dwarf may form only a few generations of stars. Each supernova then has an unusually large influence on the available gas. In the Milky Way, material from countless stellar deaths mixes together before new stars form. In an ultra-faint dwarf, one explosion can dominate the chemical composition of the next small group of stars. As a result, individual members can preserve signatures of specific early events. Some contain extremely little iron, others show unusual quantities of carbon or elements produced by neutron capture processes. These patterns help researchers study the first generations of stars, even though those first massive stars disappeared billions of years ago. Their chemical products remain inside long-lived low-mass stars. Segway 1 illustrates this value. Its wide metallicity distribution shows that it experienced real chemical evolution despite its tiny stellar population. Recent measurements of 40 members found a mean iron abundance around -2.5 and a clear metallicity dispersion, supporting a short period of enrichment before reionization and reaffirming the system as a galaxy. In a population containing only about 500 solar masses of stars, that chemical range records the effects of a limited number of early explosions. UNIONS 1 currently lacks such a detected spread. Its members appear extremely metal-poor but comparatively uniform within the available uncertainties. If future data preserve that result, the object will look increasingly like a cluster formed from one chemically similar cloud. If a hidden spread emerges, it could show that even this nearly lightless system once retained gas and produced more than one stellar generation. The question reaches into cosmic reionization as well. Astronomers want to know which early galaxies produced enough ultraviolet radiation to transform the neutral intergalactic medium. Bright galaxies are easier to observe at great distances, but the early universe may have contained many more faint systems. Individually, each produced little light. Collectively, they may have contributed a substantial fraction of the ionizing photons. The lower end of the galaxy luminosity function determines how important that contribution could have been. If the number of galaxies continues rising steeply toward very low luminosities, countless tiny systems may have played a major role. If the population turns over because most low-mass halos never formed stars, brighter galaxies must have provided more of the radiation. Local ultrafaint dwarfs cannot tell us the entire answer, but they preserve evidence of what the lowest mass early galaxies were able to do. Their ages reveal whether they formed before reionization. Their stellar masses indicate how efficiently tiny halos converted gas into stars. Their chemical histories reveal how long star formation continued and how strongly supernova feedback affected them. A confirmed galactic UNIONS 1 would show that an early halo could produce an almost vanishingly small surviving stellar population. That would extend the observed galaxy luminosity function downward and support models in which at least some mini-halos formed stars through molecular hydrogen cooling. A cluster classification would leave the lower confirmed boundary higher, though other undiscovered galaxies could still occupy the gap. The coming surveys are designed to search that gap much more thoroughly. The Vera C. Rubin Observatory's Legacy Survey of Space and Time will repeatedly image a large area of the southern sky with great depth. Simulations of its detection performance predict that it should discover satellites that are fainter, more distant, and lower in surface brightness than much of the current population. The survey will still face contamination from background galaxies and difficulty separating stars from compact distant sources, but it should greatly expand the available sample. Rubin will not simply photograph tiny galaxies as smooth objects. Many will be found through the same general method that revealed UNIONS 1, detecting statistical concentrations of stars whose colours and brightnesses match an old population at a shared distance. Repeated observations will improve photometric accuracy and may provide some information about stellar motions and variability. The Nancy Grace Roman Space Telescope can complement these searches with sharper space-based imaging. Its resolution should help distinguish faint stars from tiny background galaxies, one of the main problems near the detection limit. Large spectroscopic observatories will then be needed to measure radial velocities and chemical abundances. Discovery may become faster, while classification remains the slower and more expensive step. Some new candidates will probably be obvious dwarf galaxies because they are extended and contain enough measurable stars. Others will look like star clusters. The most interesting may occupy the same uncertain region as UNIONS 1. Each will require repeated velocities, binary monitoring, metallicities, structural measurements, and dynamical modelling. A larger sample will make the boundary easier to understand statistically. One ambiguous object can be explained by unusual history or fortunate timing. 20 objects with similar properties reveal a population. Astronomers could compare their sizes, orbits, mass functions, chemical spreads, and survival states. Distinct groups might emerge, separating dark matter-dominated galaxies from clusters rich in stellar remnants. The Milky Way may also contain completely dark subhalos that no stellar survey can find. Gravitational lensing offers one method of detecting them, because an invisible concentration of mass can distort the image or brightness of a more distant object. Stellar streams provide another possibility. A compact dark subhalo passing near a thin stream can disturb the stars, creating gaps or unusual motion. These methods can probe the structures that fail to become galaxies. The relationship between dark halos and faint satellites is therefore broader than any one record holder. UNIONS 1 represents the visible end of a much larger question. Why did some small halos form stars while almost identical ones remained dark? How much did timing matter? How did reionization change the result? Which satellites were born tiny and which were stripped down later? How much of the Milky Way's hidden substructure survives today? The answers affect our account of how large galaxies formed. The Milky Way did not appear as one complete object. It grew hierarchically, assembling through gas accretion and mergers with smaller systems. Some early dwarfs were absorbed completely. Their stars now populate the halo. Others retained enough coherence to survive as satellites. The smallest companions are not unimportant leftovers. They resemble the building blocks involved in the galaxy's earliest growth. Their stars can be older than most of the Milky Way's disk. Their chemistry can preserve enrichment from the first supernovae. Their orbits reveal the continuing accretion of small structures. Their dark matter content tests whether the cosmological model produces the correct amount of structure on small scales. If UNIONS 1 began as a star cluster, it still participates in this history. The cluster may have formed inside a dwarf galaxy that was later destroyed. It may have joined the Milky Way during an ancient merger. Its metal-poor stars could preserve information about an environment that no longer exists. The difference is that it would not mark an independent dark matter halo today. Should it prove to be a galaxy, its implications would be more extreme. It would show that the word galaxy can apply to something containing fewer visible stars than many classrooms contain people. Almost all of its mass would be unseen. The object would be defined by a dark halo and a short early episode of star formation, not by grand structure or abundant light. This would change the mental picture of a galaxy. We tend to think of galaxies as things we can see: spirals, glowing disks, elliptical clouds, or irregular patches. Yet the smallest galaxies may be mainly dark matter, with a few surviving stars scattered near the centre. The luminous component may be only a marker placed inside an invisible structure. At the same time, calling every sparse group a galaxy simply because its stars move unexpectedly would be a mistake. Binary motion, tidal disruption, and stellar remnants can all enlarge the apparent dynamical mass. The fainter the object becomes, the more carefully these effects must be measured. UNIONS. One has already demonstrated how one binary and a few improved velocities can alter an extraordinary claim. That may be its most valuable contribution. It has forced astronomers to slow down at a boundary where excitement could easily outrun evidence. The smallest systems require the largest caution, because each individual star carries so much statistical weight. One member can raise the inferred velocity dispersion, another can change the measured metallicity range, a third can shift the centre or half-light radius. The universe has not arranged its objects for convenient classification. It has produced dark halos with no stars, dwarf galaxies with very few stars, clusters dominated by dead stars, stripped remnants, tidal streams, and systems whose origin cannot be read directly from their appearance. Our categories remain useful, but they must follow the evidence rather than forcing the evidence into a tidy drawer. For now, UNIONS 1 remains beside that drawer rather than securely inside it. It is the faintest known Milky Way satellite. It is among the smallest coherent stellar systems ever discovered. It may be the surviving edge of a star cluster, whose ordinary population has nearly disappeared. It may still contain a dark matter halo that current measurements have not resolved. Further observations will decide how much confidence belongs to each possibility. Somewhere beyond the familiar disk of the Milky Way, its few detectable stars continue along their orbit. They do not look like a galaxy from any ordinary distance. They do not form a bright patch or a recognizable shape. Human observers found them only by comparing colors, motions, spectra, and probabilities. Their shared existence had to be reconstructed from data. That is an appropriate image with which to leave this tiny system. The hidden universe is not always hidden, because it is impossibly far away. Sometimes it is nearby, and simply produces too little light for us to notice, without careful searching. A dark matter halo may pass through the Milky Way's outskirts without a single star. A genuine galaxy may contain so few luminous members that it resembles a statistical accident. A dying cluster may hide most of its mass in the remnants of stars that stopped shining long ago. UNIONS one sits among those possibilities, quietly refusing to become simple. Its uncertain identity connects the smallest visible scales of galaxy formation with the enormous structure of the universe. It asks how dark matter gathers, how gas cools, how the first stars formed, how reionization ended star formation in small halos, and how the Milky Way gradually takes apart the systems orbiting around it. And here you are, listening from one planet around one star inside a galaxy that contains hundreds of billions of them, considering an object that may contain only a few dozen visible survivors. The contrast is difficult to hold in the mind. Our own galaxy is so large that light requires roughly 100,000 years to cross its disk. UNIONS, one central light occupies a region that light can cross within a few decades, yet both can help answer the same questions about gravity, matter, and cosmic history. Size does not determine scientific importance. Sometimes the faintest object places the strongest pressure on a theory, because it exists where the theory is closest to its limits. Perhaps future observations will confirm a dark halo around UNIONS 1, and the object will take its place as the smallest galaxy known. Perhaps a depleted mass function and additional binaries will settle it as an ancient cluster nearing the end of its life. Another survey may then discover an even fainter satellite, and begin the entire discussion again with 10 stars instead of 60, because astronomy does enjoy answering one question by delivering 3 smaller ones. For tonight, there is no need to force a verdict. It is enough to know that the boundary of a galaxy is not always drawn in light. It may be hidden in the motions of a few stars, in tiny differences between their chemical compositions, or in the invisible gravity surrounding them. The smallest galaxies may be less like miniature spirals and more like faint evidence that a dark structure once managed to form stars. So, as the Milky Way continues turning above wherever you are listening, allow the few old stars of UNIONS 1 to continue their long orbit without needing a final label. They have travelled together for more than 11 billion years. The question of what to call them has existed only for a very small part of that time. If you found some calm in this journey from the brightest structures of the universe to one of its faintest possible galaxies, you can leave a like, subscribe, or share this quiet exploration with someone who enjoys ending the day with unanswered questions. Then let the surveys, telescopes, and patient astronomers continue their work. There are almost certainly more dim systems waiting in the halo, some made from stars, some wrapped in dark matter, and some reduced to only the slightest recognizable gathering. The night sky may look still and familiar, but its darker spaces contain far more structure than our eyes can see. And somewhere in the direction of the Great Bear, UNIONS 1 remains almost invisible, carrying a small amount of ancient light through a universe that has not yet told us exactly what it is. Sleep well, fellow traveller, beneath a galaxy filled with hidden companions,